Hey guys, my name is Frank. I'm starting a series on how to program a tile-based platforming game called Rabbit Trap. It will feature tile-based collision detection and response, scrolling maps, loading levels, sprite animation, and interactive game objects. In this first part of the series, I'll be talking about how to build a strong foundation for the game. The concepts I'm going to explain are strongly rooted in object-oriented programming and can be used in any program to improve organization and modularity. This might seem boring, but if you use this approach, it can save you hours of editing and frustration and leave you more time to focus on fun stuff like level design and graphics. So be sure to watch this video. In this video, I'm going to talk about the model view controller approach to organizing a program and how the different components of this example work together in the main.js file. Then I'm going to talk about how this structure increases maintainability and modularity. As always, feel free to use the comment section and be sure to check out the links to the source code and working example in the video description. And if you learned something, give this video a like. So basically what I have here is just an example of a model view controller architecture where you separate out your game logic from your display logic, and you also separate out your controller logic. So I have my game logic stored in the game class, the display logic in the display class, and the controller logic in the controller class. And each one of these handles its own business, and it's totally separate from the other. So I'm not going to run into any issues with having references to the game logic inside of the display. And I'm not going to have the controller logic reference inside of the game. I'm going to have all these different components interact with each other through their public methods inside of the main.js file context. And by the way, each one of these classes is defined in its own individual file. You don't need to have your own individual files, but it makes it a lot easier to just use these different things in other applications if I choose to. For example, the engine, I might want to use this fixed time step engine inside of another application at some point, so it's nice to just store it in its own file. But anyway, what all this code does for this example is basically the game class controls a color value. Right here, that's the color variable from the game class. Basically, it just increments the different red, green, and blue channels inside of a color value to change these different colors that you're seeing on the screen. And then it will talk to the display class, which governs things like the canvas and resizing the canvas when the screen resizes and rendering. And the game will hand a color value to the display, and the display will render it on every frame, and the engine takes care of frames. As for the controller, I didn't really have anything cool to do with the controller for this example, so all it does is take user input from the keyboard and tell the user which key he or she pressed. So for example, I just pressed the A key, that's key 65. So basically what I'm trying to say is I want to keep things as organized as possible for this Rabbit Trap game, and I want you guys to kind of think about organization of code before you start developing a game, because if you just jump into things and try to mesh all this together in one big file with references going between different components, it's going to get very messy very fast. And here's an example of that I want to show you. So I define all my components, I define my engine, it's going to run at 30 frames per second, and I'm handing in the render and update function. Down at the bottom of my main.js file, I'm going to start my engine, and that's going to execute the render and update function 30 times per second until I stop my game engine. So the render and update functions I define up here, and these are them right here. So the update function is just going to tell the game to change that color value, and that's what the update function of the game does. Just increments this color value in a random direction gradually to change the color. Now the render function is also going to be called on every frame of my game loop. And inside, I'm actually going to be communicating the game's color value to the display. And I'm going to have the display object draw that color value to the on-screen canvas. So here's a great example of why this is so good. So I could just as easily write object literals to govern my display logic and my game logic. And you've seen that if you've watched my other tutorials. I'm kind of sloppy. I just throw stuff together with object literals. Here, I'm not doing that. If I had written object literals, I could put a reference to game.color directly inside of the display's render color function. Or better yet, I probably wouldn't have even had a render color function. I would just have a render method that handled rendering the entire thing. The reason I have two here is because render color draws a color to a buffer canvas, and then display.render renders that buffer canvas to the final on-screen canvas that you see. So the old version of how I wrote my code, or just the sloppy way that I write my code, would just be to put two object literals on the main JS file, and one would be display, one would be game, and I would have a reference to game.color inside of my render function, and display would just draw that color directly to the canvas. Now, the reason this is bad is because, say I want to change the name of my color variable to hue. If I go ahead and I have a reference to game.color inside of my display, and I change the variable color to hue inside of my game object, now all of a sudden I'm editing my game class or my game object to change that value to hue, and I have to go into my display object and change all the references to game.color to game.hue. Now that's a pain. I don't want to have to do that, and it's unnecessary, so I don't see why I'd do it anyway. With this method, the MVC approach, you don't actually have to have any internal references to any other components. The display only has references to itself inside of itself. The game only has references to things that it controls. So how do they communicate? They communicate just like this. They communicate through public methods. So display can only communicate with other objects like game and controller through public methods that it has. So if I come into the display object here and I take a look at render color, you can see that it just takes a color value, and inside of it, it does exactly what I said. It just changes the buffer's fill style to the specified color and draws that color to the buffer canvas. And then here's the render function, and all this is going to do is draw the buffer canvas to the final display canvas. I'm not going to get too much into detail on that, but you get what's going on here. Now, I could have just as easily gone like this inside of this function and said game.color had I made these object literals instead of classes. But that's actually really bad practice because, like I said, if I change something inside a game, it might break my display object and prevent it from working. So that's twice the editing that I'm going to have to do, because I'm going to have to change all the values in display as well as all the values in game. So this is just a much cleaner way of doing things. So basically, this is how you want your different components to interact. And just take a look at this main JS file. It's really short. Everything is super clean. I just have my two functions here, render and update, that I hand into my game engine. And here I'm defining everything. This is super clean. I don't have huge object literals to take care of, just sprawling out across my screen here in my editor. And to instantiate everything, it's real simple. I just add my event listeners for the screen resize and the keyboard inputs. And I just resize my screen initially, so my canvas fits the screen when I start up, and I start my engine and everything runs the way I expect it to. So using the MVC approach, or just separating out the different components of your game into logical groups, is a really great way to keep your code maintainable and modular. And I'm going to get into why in the next part of this video. So now I want to talk about how this approach makes things more modular and more easy to maintain. So obviously, right off the bat, it's a lot more organized. You can see that clearly. I have my different components referenced here and instantiated here in one single line each, rather than having big sprawling object literals defined. And by separating these things out into their own classes, I have the option of putting them into their own files, which makes things even more organized, because I could have all of these different classes right on top of each other in one big file. Or I could separate them like I did into their own files, and now if I want to edit the game logic, I only have to deal with 42 lines of code apparently, instead of having to search through one big file. So that's obviously one way that this technique lends itself to easy maintainability. Then there's the other thing I mentioned, where you don't have internal references to one component inside of another component. And like I said then, it's a lot easier to just work with public methods and have your components communicate via public methods, kind of like is happening right here in the render function. Display is interacting with game through a public method called renderColor rather than having an internal reference to game.color, which would be a lot harder to maintain because if I change game.color in the game object, I'm going to have to go through display and edit all of those references to game.color. So this is another way it lends itself to maintainability. Now, what about modularity? Okay, well, I've got a engine class down here, which is basically a fixed time step engine. Now, I can use this engine in any application that I want to, and it's very easy for me to do that because this is a totally self-contained class that I store in its own file. Now, I don't have to store it in its own file, but by storing it in its own file, I can very easily just reference that single file in another application, and then all of a sudden, bam, I have a perfectly good game engine for a whole nother game, and I didn't even have to write code for it. I already had it on hand. But if I were to have that game engine integrated into all my other components, it would be a lot harder for me to extract the engine components from, say, the game logic, and that just isn't very modular. The way I have it set up now is very, very modular, and it will save me a lot of time in the future when I need a game engine object. So sometimes I write my code this way. For most of my tutorials, I just throw stuff together in one file because I want everything to be there for you guys to see up front. I don't want to have to bring things in from other applications, but this is how I would go about writing a more structured application, and that's what I'm trying to do. I'm trying to write this game Rabbit Trap, and I just want it to be very structured, and I want everything to go smoothly. So using the MVC approach and separating my game logic from my display logic and my controller logic is just going to make everything go super smooth throughout this whole process. So anyway, I hope this has been a good explanation of how everything is going to be for this Rabbit Trap thing, and I hope you guys are interested in what's going to come because I expect it to be a really cool game. Before I wrap things up, I want to talk about my HTML for this example. So I actually am going to do a whole bunch of parts in this series, and rather than having to upload the sprite sheet for this example 1,000 times to my GitHub page or however many parts I have, I don't want to upload this multiple times to my GitHub page because I don't want to waste memory space. So I'm just going to use the same graphics. I'm going to use the same HTML file and CSS file, and I'm just going to write new JavaScript files as need be. So that's going to keep the memory footprint on my GitHub page a little bit smaller for this whole series that I'm doing. So anyway, the way I'm going about that is inside of my HTML, I'm dynamically determining which JavaScript files to load based on a URL variable specifying the part number. So when I come into my actual HTML page here, and I look at my URL to the rabbittrap.html file, at the end of it, there is a question mark and a 1, which is the part number for this example. Now, if I wanted to get to part 2, I would just come in and type 2. I haven't actually made part 2 yet, but that's how you would access part 2. So I'm accessing these different parts with a URL variable that is just the part. And I have a default to where if you don't specify anything, it just brings you to part 1. So that's what I'm doing. And this big chunk of code in the middle of my HTML file is taking care of that for me. So it defines all the sources I'm going to use, and that's just these files here. It gets the URL variable or that part number from my URL, that 01 after the question mark, and then it goes ahead, it checks to see if it's a viable part. If there is no part specified, it just sets it to part 1. And then it just loops through and it adds a script tag for every single JavaScript file in the application. So I'm always going to have controller, display, engine, game, main, and manifesto is just my script for the video. And I'm just going to add a new script for each one of those, and I'm going to parse together the URL or the source attribute to match whichever part I'm in. So hopefully that was a good explanation of how I'm actually getting these things in. And if you had any questions about why my HTML was weird like this, that's the reason. I'm just trying to save memory space on my GitHub page. So I'm being cheap, but I kind of figured out this cool little script to just import JavaScript files based on what part I'm in. So anyway, that is an explanation of that. This part is going to be on adding a player object to the screen and controlling him with the keyboard. This is a vital component of any game, so stay tuned to find out how it's done. In this video, I'm going to talk about the example program, what it does, and how the program has changed since part 1. Then I'm going to show you the specific code that handles creating the player, controlling him, and drawing everything to the screen. Finally, I'm going to show you my implementation of a fixed time step game loop and how it works. If you have any comments or questions, post them. And if at any point while you're watching this video you get the sensation that you're learning, be sure to support this video with a like. First thing I want to talk about is what this example actually does and how this program has changed since part 1. So all this example does is allow me to place a square which represents my player on the screen and use the keyboard to make him jump up and down. I also added some stuff in for collision detection and to make it look nice, so he changes color on every jump and he leaves a trail. The reason he's leaving a trail is just because I'm filling the background. I'm redrawing the background on every frame of animation with a slightly transparent background. So that's the reason I'm getting that trail. If I was drawing just a plain opaque background, or opaque, I guess some people pronounce it that way. If I was doing that, you wouldn't be able to see that trail behind him, but I thought that was pretty cool. And it kind of helps you visualize what's going on in every frame of animation, because each one of those squares that you see trailing behind him is drawn on one frame of animation. All right, so now that you know what the program does, let's talk about what has changed since part 1. So in part 1, I had defined my 3 different classes: my controller, my display, and my game. I also had my engine class and my main.js file. So all these are updated for part 2. That's why the file name has a O2 after it. The ones from part 1, like engine, I haven't changed since part 1. That has a part 1. So that's my naming convention that I'm using. Really, the only thing that I changed majorly besides the code that went into making the example work was I took the event listeners out of the display and the controller classes. So the key down up actual event handler function that I hand into the add event listener method in my main.js file, I'm actually defining those inside of my main file now. So this would be one that I moved out, the key down up event listener, and the resize event listener, or actually event handlers. That's what these are. So if I come all the way down to the bottom of my main.js file, you can see that I'm adding these event listeners to the window object, and I'm just handing in the methods that I define inside of my main.js file into these event listeners. So that's one of the changes I made. I decided to make that change because I didn't think that my event handling system was really something I wanted to put inside of my individual classes or my individual components. And the reason for that is a lot of times inside of these, I'm going to have to do interactions with multiple components of my game. So for example, the resize component actually needs to handle 2 different components and have them interact. It needs the display component, which handles drawing everything to the screen and all my graphics. And it also takes information from the game component, which has information about my world's height and width and my player location and stuff like that. So that's just a little bit about the example program and what it does, and a few things that have changed since the last part of this series. All right, so now I'm going to talk about how I define the world and the game object, and this is basically going to define the world that my little player square can run around in and jump in, and it's going to define the player itself. That's going to be just the rectangle that defines the player as well as the color, and it's going to handle some collision detection stuff. As you can see, I can't fall through the floor, and I can't jump or walk through the walls. So all of this is going to be handled inside of my game logic. So I'm going to come into the game part 2 file and take a look at my game class. But I'm going to keep it expanded so we can actually look at the code. All right, so the first thing I'm defining in here is a object literal called world. So inside of my game class, I'm going to have access to this world object. And inside of this, I'm just going to have my background color. And by the way, this is that transparent color. So if I come in here and I just change this to something like 0, 0, 0, 0, 0, 0, that's going to be the color for black. If I come in there and save it and then refresh my screen, now I'm no longer going to have that trailing graphic behind my player whenever he jumps. But if I come back in here and change it back, Control Z a bunch of times, get rid of that, and save, and come back here, now all of a sudden I get my trailing graphics behind my player whenever he jumps in. It looks like he has just a cool trail of fading graphics behind him. So that's pretty cool. And it's really, really easy to implement. All you got to do is draw this semi-transparent background color to erase your canvas on each frame of animation. So anyway, to get back to the world object, I just want to make a side note of this and how I did that color trailing feature. The world is just going to have everything to do with the world. So friction and gravity are going to be defined here. The player is going to be defined here. Later on, I'm going to define other objects that are going to be in-game objects. They're going to be defined here. The world boundaries, so the height and width of our level, are going to be defined here. If I were to change this, let's say I want to make the height something like 200 and have a really tall screen. If I do that and come here and refresh the screen, now you can see that I have a really, really tall game world, and that looks kind of stupid. So we're going to change it back, save, refresh, and now I'm back to my normal size. But basically, the world object just holds everything to do with the game world, including stuff like collision. So this collide object function is just going to take an object parameter, and for now that's just going to be handled inside of our game loop on every update. And I'm going to pass collide object the player object that we're defining. I'm going to get to that class later, and basically it's just going to test see is the object to the left of 0, so that's going to be the far left of our screen, and is he beyond the right side of the screen, is he above the top of the screen, is he below the bottom of the screen. It's just going to set him to where he needs to be and handle collision with the boundaries of our rectangular world here. So pretty simple stuff. Everything in this example is actually really basic. Take a look at the source code. I have it linked in the description. Here I have the update function. Now this is actually going to update everything to do with our world. So the player is going to have gravity added to his Y velocity on every frame. This function is going to be called on every frame of animation inside of the game loop. The player has his own update function, and if I come down to the player object down here, we could take a look at it. See what we got here. Update, it just adds his X and Y velocity to his current X and Y position. Go back up, see what else we got here. So we're going to update the player, we're going to add some gravity to his Y velocity, we're going to add friction, or we're going to reduce his X and Y velocities by the amount we defined in friction, which is up here, 0.09. It's just a simple pseudo-physics way to employ friction in your game. Then we have this.collide object, this.player, and this is referring to the world object that we are talking about. So that's a really simple world object. It just governs everything to do with the world, the dimensions, the player, the colors that you're seeing in there. And also in our game class, we have added, or I have added rather, the player, and it's a simple class. It's using dot syntax to kind of add this player class to the game class. And that's kind of just a way to keep things organized and almost like namespaced in there. It's not real namespacing, but by doing this, I'm not going to have a global class called player. Instead, I'm going to have to reference it with game.player like that. So if I have a bunch of classes that I'm throwing into an external context, say your game is going to run on another website and it's going to be part of the global scope of that website, you don't want your classes and stuff to be just floating around with all the other variable names and class names that other developers have defined. So it's good to try to abstract out your own class names and variable names and do stuff like put them into anonymous functions just to keep your code separated from everybody else's code out there on different websites. But anyway, that's besides the point. We define our player class here. He has a color, he has a height, he has a width, he has X and Y velocities. He has a value for jumping to determine whether or not he's jumping and he's in the air or if he's standing on the ground. We also have his X and Y position. And since I'm just being lazy and I'm not loading him in from a level map, I'm just going to define his values all right at the start here when the player object is instantiated with the new operator. So now I go into the prototype and I have a couple different functions that govern how he moves. I have the jump function. Basically just says if he's not jumping, then we're going to change the color and we're going to make him jump down here. So pretty simple. This is the code to get a random color, and I'm not really going to go into that, but basically it just makes his color change every time he jumps. Every time I press the up arrow on my keyboard, the jump function is called on the player and this code runs. Pretty simple. Same thing for the move left and move right functions. These functions are going to be called in my main JavaScript file. I'm going to take a look at that in a second. And all it does is just add half a pixel to his X and Y, or X velocity, depending on which button you press. If I press left, I'm going to subtract 0.5 pixels from his X velocity. If I press right on my keyboard, I'm going to add 0.5 pixels to his X velocity. And then finally, that update function, that's just going to add his X and Y velocity to his X and Y locations in the canvas, respectively. So now let's take a look inside of the main.js file and see where all of these are being employed, which is going to be inside of the update function. So the reason I have my update functions all over the place, I have one for my player, I have one for my world, and I have one in my main JavaScript file, is because I'm doing different things inside of all of them, and I want to keep all of my objects as self-contained as possible. So for instance, the player object, his update function is really simple. It just handles stuff that has to do with the player. My world's update function only handles stuff to do with the world. So this.world.update is going to be this function right here. The world's update function only has to do with things inside of the world. The main JavaScript file has an update function that handles the controller as well as the game. So I'm mixing these two major components of my game's logic inside of this one method inside of my main.js file. And that's kind of where I want everything to communicate. I don't want to have those internal references pointing to other components inside of my game. I want all of my code to be very self-contained, and when I have it interact with other components inside of my code, I want it to be in a safe context, kind of like the main.js file. That's where I'm going to do most of my editing. So anyway, I'm getting information from the controller. I'm just saying, is the controller being pressed? Are these keys active on the keyboard? And if so, I'm going to execute a corresponding function on my player object. Finally, I'm going to call game.update, and game.update is going to go ahead and call world.update. World.update is going to call all of this stuff, and that's going to give me these nice cool physics and take care of all my numbers and player position and velocity and whether or not he's colliding. And that's going to take care of all of the physics logic in my game. It's also going to change the player color. All right, so now I just talked about what actually makes the game logic work, and that is, of course, the game class itself, stored in the game.o2 file. So now I have to talk about how I'm getting keyboard input and relaying that to the game class so it can actually take that input and do something with it. So I just showed you inside the main file here that I'm conveying the keyboard's input via the controller object to the game object and telling the game object to do something with the player's position, like move left, move right, or jump. And that's all going to happen depending on what the controller object is doing. So let's take a look at the controller class and see how that works. So the controller class just has three objects here, a left, right, and up object, and those objects are going to be controller.buttonInput classes. So let's take a look at the button input class and see what it is. It's really, really simple. All it is an object that has two Boolean values inside of it, one called active and one called down. Now, active is going to hold the virtual state of our button. So I'll get into that in a little bit because it has to do with jumping. And down is going to refer to the physical state of our button on the keyboard. So if I physically press the up key down, down is going to be true. And if I hold that key down, it's going to remain true. The active value, however, is going to depend more on my actual game's logic. So just remember, keep in mind that down refers to the physical state of the button on my keyboard, and that's what that is going to track. And active is just going to track what that value is of my button object inside of my game's code or my game logic. So now that you know what the button input class is, these three objects are going to be button inputs, and this key down up event handler function is going to be called every time I press a key on my keyboard, whether I press it down or it comes back up. This is going to be called. It's going to check to see what the event type is, key down or key up. So when I press a key down on the keyboard, the type's going to be key down. When I release that key, it's going to be key up. And depending on which one it is, it's either going to be true or false. And then I'm just going to use the get input method of my button input class and hand in that down value, which is either going to be true or false. And that's going to look like this. It's just going to say if the key tracker or the button input object, if that currently is down, the state is currently down, or if the state is not equal to whatever we're handing in, then we're going to set active equal to whatever we're handing in. And we're just going to set down equal to whatever we're handing in, because that's going to be the physical state of the button. Pretty simple, maybe not so simple. Take a look at the source code and fiddle around with it, because that's really the best way to get an idea. I'm just here running over everything. I'm trying to get it done quick because this video seems like it's going to go long. I don't want it to go too long, but basically this is a controller class, just takes keyboard input, and I'm adding the event listener for the controller component inside, not my engine, but inside of my main JavaScript file. At the bottom, if I come all the way to the bottom, you can see I'm adding the key down and key up listener to the key down up function, which I'm defining also inside of my main file, and that is just going to call the controller's key down up method and hand in the event.type and the event.keyCode, which we use to determine what the type is, whether it's a down press or an up press, and the key code is just going to determine which key on the keyboard I'm pressing. So 37, 38, and 39 are the left, up, and right arrow keys on the keyboard. So basically this controller class just gets keyboard input, and then we relay that input to the game component right here in the main.js file inside of its update function, which is called on every frame of animation, managed by our engine, which I'm going to talk about later on in this video. So really simply, just checks to see if the left, right, and up keys are active, and then it goes ahead and it calls a player movement function. So move left, move right, or jump. So where the active value comes into play here is when the player is jumping. So notice that I'm actually setting the virtual state of the controller.up button input to false. I'm changing the active value to false. So that's going to give me the ability to press my key once and hold it down and not have my player jump again. If I were to come in and comment this line of code out like this and just go like this, comment this guy out, save my file, come over here to my browser, refresh. Now I'm just going to jump up and down continuously. Now this might be desirable for some people. For some games this might be what you want, but for other games you're not going to want to keep on jumping just because you have the key pressed down. So if that's something you want in your game, not having the player jump up and down continuously as your button is pressed in, this controller class right here and these button input objects here with this dual virtual and physical button state tracker objects here, these Boolean values, this is going to allow you to prevent your player from just jumping up and down continuously, and you're going to get functionality that looks like this instead. You're just going to be able to jump one time and only jump when you press the key rather than jumping just continuously if you have the key held down. Alright, so now that you know how to define the player object and the world object in our game class, and you know how to get user input to actually control this guy and move him around the screen, the only thing left is how to draw this guy. So how we're drawing the player object and the world itself to this canvas element is with the display class. So inside of the display class, I just define a buffer and a context of my canvas. So these are two 2D rendering contexts, canvas rendering contexts. Context is the rendering context of the on-screen canvas that you see on screen. Buffer is just an off-screen canvas that is going to be sized perfectly to match our world height and width. So if we come back into our game and scroll down here, the buffer canvas is going to be sized at 72 pixels high and 128 pixels wide. And that is actually going to happen all the way at the bottom of our main.js file. And the reason for that is just so everything scales the way it should. So I'm setting that up right here in the initialization portion of my main.js file. So let's get back into display and talk a little bit more about it. So I've added a couple different functions. I have the fill function or method. All it does is take a color and draw it to the buffer, which remembers the off-screen canvas, which is then drawn by the render function to our on-screen canvas. It draws this off-screen buffer canvas to the on-screen display canvas that you actually see in the browser window. So the fill method just fills the buffer with color. Render renders that buffer to the screen. Draw a rectangle just draws this rectangle here. That's what I'm handing in terms of X, Y, width, and height, and color. And it just draws that to the buffer as well. I'm actually rounding down the X and Y positions of the rectangle that I'm handing in. This way it doesn't render it on a half pixel. So let's see what happens when I take this code out. But first, let's take a look at what this guy actually looks like moving around the screen. So pretty smooth. Nothing weird going on. All the edges look pretty straight. If I come in here and I just put in X and Y though, let's take a look and see if anything changes. As you can see, it looks a little bit funky. I mean, it's hard to tell because I have this background. Let's actually go in here and change the background color of my game to something else here. Let's make it black instead. 0, 0, 0, 0, 0, 0. That's going to give me black. I'm going to come in here, refresh my screen. Take a look at the player character. You see how his edges are kind of messed up? They're kind of wavering a little bit. Kind of looks like he's just fading around instead of just sitting on the exact pixel he's meant to sit on. Well, that is actually because he's sitting on half pixels from time to time, and you can fix that by rounding down the values you pass into your draw method. So we can go from this, which looks a little bit funky, to this, which now looks really sharp and not so funky at all. It's basically the best we can get on a HTML5 canvas. So now let me set back my background color to the way it was before so we could have that nice fading effect that follows the character around. Refresh my screen. And so that's what I'm going to use to draw my rectangle to the screen and round him to the nearest full pixel location with math.floor so he doesn't get that weird blur around the edges. Now let's take a look at the main.js file, and that's where all of these are going to be called. Actually, I think inside of... Actually, no, I'm wrong. Let's just take a look at the main.js file and see where these guys are called. I think it's going to be inside of the render function. I haven't looked at this code in a little bit. So we have display.fill. And by the way, the render function is going to be called by our game engine, which is our game loop on every frame of the animation. So 30 times every second. So we call display.fill. That's going to fill our background color with this nice dark gray here. We're going to call draw rectangle and hand in the game.world.player, which is a rectangle. We're going to hand in all those values as well as the color value. And finally, we're going to call display.render. And that's going to draw the buffer that we just filled with the background color and drew the rectangle to. And we're going to draw that buffer to the final display canvas. Now, one more thing I want to talk about here, because this is pretty simple stuff, is the resize functionality. So the resize functionality is going to take care of scaling my on-screen canvas. It's also going to take care of keeping the aspect ratio of the game world, which you remember has the height and width coordinates. It's going to keep that aspect ratio from the game world and the buffer to the final display canvas, so we get a nice square rectangle every time. So what's important about that? Well, if we come down here, I told you that we're going to set our buffers canvas height and width to the game world height and width. Now, if I were to change this and say height times 0.5, obviously that would warp our game a little bit. So let's take a look at that and what that looks like. Oh, kind of cut off half the world, but you can see that when I jump up the player is actually a lot taller than he is wide by about twice as much. So let's set back that back to normal and go ahead and take a look at the resize function, which I'm adding to the window that handles all of that stuff. So resize is right here. It's going to call display.resize, and it's going to hand in document.documentElement.clientWidth and client height. It's going to subtract 32 pixels from both of those to give us this nice 16 pixel margin on either side of our display canvas, which I have to refresh so it goes back to the way it's supposed to be. So that's what that's doing, those 32 pixels. And then it's going to hand in an aspect ratio of our game world, which is going to be just the height divided by the width of our game world. So now let's take a look inside of the display objects resize method and see what it's actually doing. So here I am inside of the resize method, and as you can see, it's not super complicated. It's actually pretty simple. It's basically just going to say if the height and width ratio that we handed in from document.documentElement.clientWidth and client height minus 32 pixels to give us that nice 16 pixel margin on each side. It's going to say if that ratio is greater than the height width ratio of the world object, the game world, then if the screen's height width ratio is greater than the height width ratio of the world, then we're going to set the canvas's height to the width times the ratio, and we're going to set the canvas's width to the width of the screen. So right now we have a max width scenario. Otherwise, we don't have a max width scenario. We have a max height scenario, and it's going to set the canvas's height to the max height, and it's going to set the width to the height divided by the height width ratio. So this code is basically going to allow me to do this. If I come in here and I change the scale of my window, as you can see, it's always going to keep it centered. Right now I have a max height situation, and I have a shorter width in my game world, but the aspect ratio remains the same. And here I'm going to go back down. Somewhere around here, I'm going to change over from a max height situation to a max width situation. And now you can see my display canvas gradually getting smaller in height. So that's pretty cool. That's the display function. Takes care of resizing the canvas and maintaining that nice aspect ratio so our game can scale nicely across many different devices. Alright, so now I'm going to do a brief run through of my fixed time step game engine, and this is the game engine class. It's in the engine file. I haven't changed it since part 1 of this series. It's exactly the same as it was, although I did add in this accumulated time variable definition because it wasn't in here. It was actually being added later right here, so I just fixed that, but it's basically exactly the same. So what a fixed time step game loop does is it causes your game to update and draw at a fixed rate as time passes. And it does that by taking a time step value, which in this case is going to be 1000 divided by 30. If I come over to my main.js where I actually instantiate this, I am passing 1000 divided by 30, which is roughly 33.3333 repeating forever. And that is going to be the number of milliseconds that I'm going to call render and update on. So every 33.33 milliseconds, I'm going to call render and update. And the render and update functions are just right here. You've seen them throughout this video. And they're basically just going to update my game logic and render the changed game state to the screen. Let's hop back inside of the engine and talk about this game loop some more. All right, so we've got our time step, and that's going to be, in this case, about 33.33 milliseconds. And so every 33.33 milliseconds, I'm going to call the update and render function that I passed in. They're going to be stored right here. And I'm going to keep track of how much time has passed in the accumulated time variable. So every time 33.33 milliseconds passes, hopefully our game is updating close to that. But anything that overflows is going to be stored in accumulated time. So let's say 33.33 is our minimum time step, and that's exactly what it is. But let's say request animation frame, which is what we're using to update our game logic, fires at 40 milliseconds. Now we're going to have about, what is that? 6 something, about 6 milliseconds left over, and we're going to store that in accumulated time. And when accumulated time reaches our time step, or 33.33, we're going to update or call update one more time. So basically, we're storing all the time that passes in accumulated time, and we're just taking bytes out of that accumulated time. We're taking 33 millisecond bytes out of our accumulated time. The time value is just going to be the last time our run function executes, and this is just going to be the looping function. This is going to be the function that loops over and over again. A lot of game engines will call this cycle. Some call it loop. I'm just calling my run because engines run, so this is going to be one run of the game loop. So inside of the run function, we're adding the current timestamp that's handed to us by request animation frame. We're subtracting the current time or the last time our game executed from the current time, and we're adding that to accumulated time. So let's say that the last time our game executed was at 100 milliseconds, and we're just now getting in a new call to the run function from request animation frame, and it's going to happen at 140 milliseconds. So we're going to have 140 milliseconds minus 100 milliseconds, and 40 milliseconds is going to go into accumulated time. So now we have 40 milliseconds in accumulated time. We're just going to set the new most recent time value to the current time value, but just remember 40 milliseconds in accumulated time. Here is where the fixed time step game loop really shines, because this, well, actually, this is just a safety I'm not going to talk about, but this is where it really shines, the while loop. So remember, we have 40 milliseconds of accumulated time, and we have our 33, I'm going to round that down to 33, our 33 milliseconds in our time step. So 40 is greater than 33. So while 40, or our accumulated time, is greater than our time step, we are going to reduce our accumulated time by the time step. We're going to call update, and we're going to set this updated flag to true, but don't worry about that too much. So then we're going to loop again and see if that's true again, and we subtracted 33 from 40, so that's going to give us 7, and 7 is no longer greater than our time step, so we're not going to update again. But let's say that accumulated time was equal to 70. Okay, so now we have 70. 70 is greater than 33, so we're going to call update. Then we're going to try to loop again. Well, 70 minus 33, what is that? 47? Is that accurate? Anyway, 47 is still going to be greater, whatever it is, it's still going to be greater than 33, so we're going to update again. So even if we didn't have another request animation frame event fire, and we didn't update the screen again, we're still going to be updating twice on the next time request animation frame fires and gives us a new run command, or we're going to call run again. So we're going to be keeping up with time no matter what happens. So even if our game runs really slow and laggy, it's still going to keep up with time, and it's going to run at the same rate basically on any device regardless of how slow it is, unless the device is so slow that it just can't handle the game and then it will crash. But that's not something you really should worry about unless your game is crashing all devices. But if your game is just crashing the computers from 1995, then you shouldn't worry about it. But basically, the fixed time step game loop just says if too much time has passed, or if a certain amount of time has passed, we're going to update our game at whatever rate we want it to update until we have caught up with however much time has passed. And that's a really great functionality of fixed time step game loops, and it's a great reason to add them in to any game that you're writing. So now down here we have the updated flag. Basically, we turn that flag on, we set it to true anytime we do an update. And then if it is true, if we have updated, then we're going to call the render function, and that's just going to draw our game. So why is this good? Well, let's say accumulated time only has 20 milliseconds in it, but we need 33 milliseconds to justify an update. Otherwise, we'd be going faster than we want to update. Well, if that's the case, then this never fires, we never update our game, and if we don't update our game, nothing has changed, and anything we draw is just going to be a waste of CPU or GPU. So we don't want to draw anything that hasn't been updated or changed. So if no update has occurred, updated stays false, and we don't draw. And finally, inside of the run function, we just make another call to the handle run method. And the handle run method is just down here. It's just an arrow function that calls the engine.run method. Now, the reason I'm using an arrow function is because if you've worked with event listeners or request animation frame before, the this keyword inside of whatever function you hand into your event listener as your event handler, or request animation frame as your response to a request animation frame event firing, is going to point to the object that you request the frame or add an event listener to. So in this case, it's the window. So I don't want this to refer to window. I want this to refer to my actual engine object. So by using this arrow function, I can actually make this refer to my engine object rather than the window. So that's the only reason I have that kind of set up as an arrow function there, to make sure that the this keyword is referring to engine instead of window. Otherwise, I would have to have a reference to engine inside of the engine, and that just is really, it just seems really sloppy to me. So I set up the arrow function, and that's what that does. And anyway, I hope that was a good explanation of a fixed time step engine, and probably wasn't the best. I was kind of going through it really fast. It's really cold in this room where I'm recording, and I'm like freezing to death. So don't hold it against me. I should turn up the heat, but you know, just I'm doing what I'm doing here. So hopefully that was a good enough explanation of a fixed time step game loop. And if not, definitely take a look at the source code. I commented everything in here so you guys can get a better understanding of the code as you read through it line by line. In this video, I showed you how to lay the groundwork for any platforming game. So far, I've implemented keyboard input, simple platforming physics, scaling for multiple devices, and a fixed time step game loop to handle updating your game at a consistent rate no matter what device it's on, which is perhaps the most important thing you could take away from this video. I'm going to show you how to draw a tiled background from a one-dimensional tile map. I'm going to talk about the example program and what I've added since part 2. Then I'm going to talk about how to load the tile sheet image and store it in a tile sheet class. Finally, I'll show you the tile map in the game class and how it's drawn. Alrighty guys, let's take a look at what has changed since part 2. If I come over here in the browser, first I'm going to go ahead and I'm going to pull up part 2 so you guys can see it. And that is right here. I'm going to press enter, load up part 2. And this is part 2. So as you can see, I have some jumping physics, I get keyboard input, but there's no tiled background. And to make this game, I'm definitely going to need a cool tiled background. So let's go over to part 3 and check out what we've done there. Alright, so this is part 3. And as you can see, it's a lot better. I still have the same game physics where my character jumps around and moves around. Same fluid physics, exact same physics code. The only difference now is the world is a different size, and I have a tile map inside of it. Also, the color of the character is just a solid white and gray. The reason I did that was to more closely resemble the player sprite we're going to be using, which is this little rabbit dude. And basically that's it. That's all the changes that have happened in part 3 since part 2. The files where the changes occurred are display, game, and main. Everything else, I'm using the controller class from part 2. If I come into my directory here, I'm going to be using the controller class from part 2. And I'm going to be using that file, and I'm also going to be using the engine class from part 1. But this is part 3, and these are the only 3 files that you need to worry about if you've already watched part 1 and 2. So anyway, on to the rest of the video. So the first thing we need to worry about for this application is how we're going to get our sprite sheet PNG image into our JavaScript so we can actually do something with it and have it render over here on the screen and show up on the background of our canvas element. So first we need to define some sort of container for our sprite sheet image and its different variables, and we do that inside of the display class. So here's my display class. It's one of the files that has changed since part 2, and inside of it I define a class called tile sheet. I come down to the bottom here. Here's my tile sheet class. It's just a really simple object. It has an image inside of it. This image object is going to store our tile sheet or our sprite sheet, and then it records the tile size, and I'm just going to hand in 16 because each one of our tiles is 16 by 16 pixels, and the number of columns in our tile sheet. So I think that's 8 off the top of my head, but if we come over here and we actually count them, we're going to have 1, 2, 3, 4, 5, 6, 7, 8 different tiles. It's kind of hard to tell, but there's 8 tiles or 8 columns in this map. 8 tiles across or 8 columns, not just 8 tiles in the map. Obviously, there's more. But so we have to define this tile sheet class, and it's just going to have an image, which is going to be our image. It's going to have the tile size, and it's going to have the number of columns in our tile sheet image. Now that we have this, we can actually go about loading this PNG image into our JavaScript so we can do something with it. Where that happens is the main.js file for part 3. So if I come down to the bottom of my file here, you can see that I am setting the image of my tile sheet object in the display class. I'm setting the source of that image to the rabbittrap.png, and that's going to start loading the rabbittrap PNG image here into the tile sheet object's image. And when it's done loading, it's going to fire this event listener for loaded. So it's going to say, okay, my image just loaded. I have an event listener for that. Let's call this function, the event handler function, for a load event there. I'm going to resize the screen. That's just going to resize the browser window, or not the browser window, but resize our canvas to fit the browser window rather. And it's going to call engine.start. That's going to start our game loop off, and then we're actually going to be able to use that graphic, because if we start our engine before the graphic is fully loaded, we're going to try to draw graphics that just aren't loaded yet, and that's a problem. So make sure that your graphic is fully loaded with an event listener for load before you actually start your engine. Also down here, this extra parameter, once : true, that just tells this event listener to only fire once, and after it's done, it just junks it. Sends it to the trash, sends it to garbage collection. We don't have to worry about removing this event listener from our tile sheet image, because this parameter here just takes care of it. Alright, so now that we've loaded our tile sheet image into our JavaScript, we actually have to get these individual images out of this sprite sheet or tile sheet. We have to draw them to different locations on the canvas to create something of a tiled map, like you see here. So how do we do that? Well, it starts out in the game class, and I have a map inside of my game class, inside of the world. And basically, it's just a big long array of values that point to different locations in the tile sheet. So the best way I can explain this to you is by just giving you an example. And I'm going to look down here in the bottom right of my numeric tile map at these 3 values, 1, 43, and 10. Now these values correspond to locations inside of my tile sheet graphic, and they also correspond to these locations on the map. So this is the 1 tile. This here is going to be the 43 tile, and this over here is going to be the 10 tile. And as you can see, you can kind of make that connection. Those 3 tiles are going to be in this bottom right-hand corner of the map. So now let's take a look at these tiles inside of the sprite sheet itself. We're going to have 1, so that's going to be, for this example, it's going to be at position 1 in our map. Normally I start at 0. I start counting at 0, but for this example, I'm going to start counting at 1. So tile 1 is just going to be this corner tile, and as you can see right here in the map, it is that corner tile. These 2 tiles are the same, so tile 1 is just going to be this one right here. And if you think about it, it makes sense because this is the first tile index in the map. So it would just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And remember, this is tile 10. We have our 10 tile right here, and it's just a plain clear brown tile. And if I come back to my map, you can see that that is in fact valued at tile 10. So now you kind of understand, or hopefully you understand, the correlation between these values in a one-dimensional tile map and the images on screen, as well as the locations of those images in the tile sheet image itself. But just because we have the map doesn't mean we're actually drawing this stuff to the screen. We actually have to write a function for that, and that function is going to be inside of the display class, and it's a function called drawMap. And it's just going to take the map, which is just that array of values, so it's just going to be this. I'm going to hand in, and the number of columns in the map, and we have 12 columns in our map. I define that here, 12 columns. If you count, I actually have 1, 2, 3, 4, all the way to 12 columns inside of my map. If you look at the screen, you can count 12 tiles across. So this draw map function is just going to take the map and it's going to take the columns and it's going to loop through every single value in the map. So it's going to loop through every single number right here and it's going to get the value there. I subtract 1 from it and that's going to, if I don't subtract 1, this is what happens. If I just add 0, let's take a look real quick and see what happens. And I'll show you a really simple way to remedy this, which I didn't use because I used a tile map editor to make this because I have really complex tiles here. But this is what it looks like, and it's because all of my tile values are offset by 1. Now I set it back to -1. The reason for that is in my tile map, these are all 1 higher than they should be. So this should actually be 17. This should be 48. This should be 49. This should be 31. They're all offset by 1. That's just because the tile map editor I use, which is tiled, exports the comma separated values starting at 1 instead of 0. I didn't feel like going through and changing all these, so hopefully this doesn't throw you guys off too much. Don't worry about it. When you make your maps, just make sure you have the right values starting at index 0 in your tile sheet. So basically, instead of this being 1, it would be 0, and you start counting from 0. But if you want to use a map editor like tiled, and you don't mind just having that offset, it's really simple. All you have to do is subtract 1 from the tile value, and you're good to go. So anyway, that aside, let's get into how I'm actually placing those images from the source onto the buffer, and then drawing it on the screen. So I get the different values, or I get the value of the specific tile in the map that I'm looping over. I get the source X and Y position that I'm going to cut it out of the tile sheet at, and that's what this code right here does. It just takes the number of columns in the tile sheet, takes the value, that gets the column, and then you multiply by the tile size to get the actual position to cut out of inside of the tile sheet image. Oh, didn't mean to do that. But that's basically just getting the X position to start cutting out of. Come back in here. Then we have the Y value. That's going to get the Y position to start cutting out of. And then when you get the source, you're going to hand in the source X and Y, which is just these 2 values here, and the tile height and tile width, which I just have 1 of. It's tile size and it's 16 pixels. So source X and source Y are going to get me to the appropriate tile. Say I am at tile 8. That's going to put me right here. It would actually be a value of 7, but that's going to put me right here. And then I'm going to cut 16 pixels wide and 16 pixels high. So the Y value would be 0. The X value would be 128 minus 16 to get me right here to the left side of this tile. And then, because 128 is the width of my map, and it's just going to cut this tile out. So pretty simple. Come back here, display, look at the rest of this. Destination, it kind of looks like the same kind of mathematical formula. I'm just using the number of columns in my game world, which you remember is 12. So that's the number of columns in this map. And I'm multiplying that by 16 as well. Now I guess I should be using the game.world.tile size, but I'm just using 16 for both, so I guess it doesn't really matter. And then finally, you're going to use this information to cut the appropriate image out of your tile sheet image and draw it into your buffer, which is then going to be drawn to the final on-screen canvas. So you're just going to say, I want to draw an image to my buffer from the tile sheet image, and I'm going to cut the image out of the tile sheet out at source X and source Y, and tile size width and tile size height. I'm going to draw it to the buffer at destination X and destination Y at the 16 by 16 width and height. So that's all that does. And then if I come out here into my main.js file and I come down to the, or up rather, to the render function, you can see that I'm calling the display.drawMap function. I'm handing in the game.world.map and the game.world.columns into that function. And that is how you draw all those tiles to the game screen. I talked about how to load a sprite sheet image into your JavaScript, how to create a tile map array, and how to draw tiles from the sprite sheet to the display canvas. If you're worried that there was a lot of code I didn't cover, don't. All you need to know is how these basic components work together in order to build them yourself. Chances are your application structure will be different from mine, so don't focus too much on what I didn't show you, and instead try to build the components I'm talking about into your own application. This stuff really works, and if you need the source code, you can find it on my GitHub page. I'm going to show you, the aspiring game programmer, how to add pixel-perfect, professional quality, tile-based collision detection and response to a platforming game. I'm going to talk about what's changed since part 3, then I'm going to go over the 3 main components of my collision system. There's the broad phase, the routing function, and finally the narrow phase. Let's take a look at what's changed since part 3. So this is part 4. It looks just like part 3 for the most part, except now I have collision detection and response between my player character and the game world. So as you can see, I'm moving smoothly across the tops of the tiles. I'm jumping up along the sides of the tiles. I'm not getting hung up on any of the edges, anywhere I can jump through the bottoms of these platform tiles. Basically, I have pixel perfect tile-based collision detection and response, and everything looks and works the way you would expect it to in a tile-based platforming game. So now that you know what the example is all about, let's take a look at what's changed in the code. So the only 2 files that have changed since part 3 are the game file, which holds the game class, and the display file, which holds the display class. Display had a minor change since part 3. If you remember part 3, I had an issue with the export values for my tile map because I used the tile map editor, and all the values were offset by 1. So I just changed this function and I changed my tile map values to what they're supposed to be. So I got rid of the offset. As you can see, I have the comment no longer subtracting 1. Take a look at part 3 so you can see what I'm talking about. Also in here in the draw player class, I changed math.floor to math.round in this line and this line here. And the reason is because it just rounds my player to the appropriate spot that he's going to be drawn in more smoothly. So those are 2 really minor changes in the display file. Inside of the game file, a lot has changed. I've added the collider function. I've added my collision map, which is this guy right here. A collision map is different than the graphical map for the tiles themselves that you see on the screen. These are for the collision shapes. Down here, I've amended my collide object function inside of the world class to do the broad phase collision detection and response that are these functions right here. Then I've also added the collider class. The collider class takes care of the routing function as well as all of the narrow phase collision methods like collide platform bottom. So collide platform bottom would be called whenever you physically collide the top of the player with the bottom of a platform. So I'm jumping up, and collide platform bottom is firing every time my player hits his head on the bottom of that tile there. So that's what that does. Then I've also added a base class for the player object called object, and that's nested inside of game.world. The object is basically just a simple rectangle class, and I'm going to talk about xold and yold and why we need those later on in a different part in this video. But basically, the object class is just the superclass of the player class. Now, basically, the player is going to inherit all of these values from object, and it's going to get all of these neat little helper functions to get the different sides of his rectangle. So that's all that does. And then down here, you can see I'm actually extending the object class inside of the player constructor. And down here, I'm actually extending the player prototype off of the object prototype with object.assign. So those are all the changes in part 4. Stay tuned for the rest of the video. There are 3 main components to this approach to tile-based collision detection and response, and those are the broad phase, the routing function, and the narrow phase, and they're all centered around having a collision map full of collision tile values. Each value represents a different shape or collision shape. So for instance, if I hop over here, I can jump through the bottom of this tile but not fall through the top of this tile here. I can collide with the bottom, I can collide with the right side, and I can collide with the top of that as well. This tile over here, these two, I can collide with the left side. So all of these tile values correspond to collision shapes that have different sides. So the broad phase gets what tile my player character is standing on. It determines what the value of that tile is that my player character is standing on, gets that value from the collision map. It then hands that value as well as the player object into the routing function. the routing function checks the value in a switch statement, and it says, okay, well, let's check, for instance, I'm standing on top of tile 1 here. This is tile 1. So the routing function would say, okay, you're colliding with tile type 1, and for tile type 1, I'm going to call a certain set of narrow phase collision detection and response methods. So the broad phase determines what the tile value is, the routing function determines which narrow phase functions to call, and the narrow phase does the final collision detection and response. And that's how the system works. So stay tuned, and I'm going to go into the code that makes that stuff work in detail. Alright, so now I want to talk about the broad phase collision method, and that is going to be the collide object function, which is located inside of the game.world class. So I'm going to come down here and show you what this broad phase does. The whole function, all it does is first it checks for collision with the outsides of the world, and that's going to be this right here. That's from part 3. That's pretty simple stuff. And then the other thing it does is it checks all of the different corners, all 4 corners of our player character. So I have these 4 chunks of code. I have one here for the top left, I have one for the top right, one for the bottom left, and one for the bottom right, and that's the end of the function. So this is the entire broad phase, just these 4 chunks, and this chunk up here, which does collision with the boundaries of the world. So let's take a look at the first chunk that tests for broad phase collision with the collision map with the top left corner of our player character. So what these are a row and a column value inside of our collision map. So top is going to be the row that the top side of our player is in, and left is going to be the column that the left side of our player is in. So this is going to be the top of our player, this is going to be the left side of our player, and this is going to be the row that the top is in. Now if I move the player over here, this is going to be the row that he's in. And if I check the left side, this is going to be the column that he's in. If I move him over here, now the left side of the player is in this column. So pretty simple. The math that we use to get the row and column and convert it from the physical XY position of the player to the one-dimensional index or of a row or column value. It's not really one-dimensional, it's two-dimensional, it's just simplified. Basically, you just get the top of the object, which is the Y position of the top of the object. You divide by tile size. That gives you the row of the top. And then you do the same thing for the column. You just get the left side of the object, which is right here. You divide it by tile size. That's going to give you the column value. And then you're going to go ahead and convert those, the row and the column, into a index inside of our map array, our collision map array. And you just do that by multiplying the row by the number of columns inside of the collision map. Ours was 12. And then you add the column that the player is standing in. So that's the row of the side of the player multiplied by the number of columns in the collision map plus the column of the side of the player. Pretty simple. And then you go ahead and you hand in that value as well as the row and column positions of the tile multiplied by tile size to give you the actual X and Y position of the tile. So for instance, if I was going to get the top left of my player, that would be right here. He's inside of this tile. The top and left values multiplied by the tile size is going to give you this position right here, which is going to be the X and Y position of the tile. So we're going to hand all that information into the collider's collide method, and that's going to be the routing function. You're going to hand in the value, you're going to hand in the object, you're going to hand in the left side of the tile, and you're going to hand in the top side of the tile. You're also going to hand in the tile size. And then you just go ahead and you do this for every corner of the player. So we just did the top left. Down here we're going to do the top right. Then we do the bottom left. Bottom left, there we go. And we do the bottom right. And we just do that for all 4 corners. Now you might be thinking, well, you're redefining some values that you're reusing. So why not just define, for instance, here we go. Let me find a good example here. Right. So this is checking the top right corner, right? This right here. And this is checking the bottom right corner. Well, I'm defining right 2 times, but why would I do that? Well, the reason I'm doing that is because here I'm defining right, and I'm checking for collision. If I have a collision and I respond to it, my player character is going to move. And right, as I defined it here, might not be the same anymore. So down here, when I'm getting the right side of the player again, I'm not going to want to use this old value for right. I'm going to want to get the right side of my player again because it might be different than it was when I checked collision with the top right. So when I check collision with the top right, if there is in fact a collision up here, it's going to move my player. And then when I check, oh, this is the top right. I keep getting confused there. But then when I check the bottom right, if I moved, that value is going to have to be redefined to get the appropriate new location of the player's right side after he had collision resolved with the top right corner. So this is the broad phase. It's not as complicated as you think. It's really simple. The math is really simple. You're just getting a value out of an array based on a player's column and row, or row and column rather, and then you're handing all that information into the routing function. We're going to take a look at the routing function in the next part of the video. Now let's take a look at the routing function. So I'm going to come down here to the routing function, and that is going to be in the game.world.collider class, and it's going to be called collide. So the collide function is my routing function, and all it does is it takes the tile value, the object, and the tile's x and y position, as well as the tile size, which is the tile's width and height, and it takes all that from the broad phase and it hands in the value of the tile into a big switch statement, which then routes you, and that's why I call it a routing function. It routes you to the appropriate narrow phase collision methods, and it also does some tweaking to the tiles. So for instance, case 1, if I move my player down here, I'm actually going to be standing on a 1 tile. I know for a fact this here is a 1 tile, and it's going to call collide platform top, and it's going to hand in the object, so that's going to be my player character. It's going to hand in tile Y, not tile X, because we don't need it in this case. We just need to know what the top of the tile is going to be. Now, if I want this to be a little bit lower, say I want to make a half tile, I'm just going to hack this right now, but I'm going to put in +8, and I know for a fact that 8 is half of my tile height. So that's going to be, oops, didn't mean to do that. That's going to be my change that I made. I saved my file. I'm going to refresh my screen. Now, as you can see, all the 1 tiles that I'm colliding with are going to have half height. So this tile right here, I'm now going to be colliding with a value that's a little bit lower. Interesting. So I can take my narrow phase functions and I can tweak them a little bit inside of my routing function, and that's going to give me the ability to create a whole bunch of different tile types however I want. So all the different shapes are going to be defined basically inside of the routing function, and all it really does is gets the tile value and links it to a certain set of narrow phase functions. Let's take a look at, let's see what I got here. Let's take a look at something a little more complex. First, I'm going to have to see what tiles are what, because I can't think right off the top of my head what those values actually stand for. But if I look at my map, I'm going to come over here to a 13 tile, and that looks to be at the left side of this T right here. So 13 is going to be, oh wait, I forgot to refresh my screen. Let's refresh and get functionality back to normal. So 13 is going to be this tile right here that I'm standing on now. So let's take a look in the routing function at the 13 tile. All right, here we go. It's going to call the methods collide platform top, collide platform left, and collide platform bottom. And the reason for that is because I'm going to collide with the left side of this tile, collide with the left side, maybe if I can actually hit it, collide with the left side, I'm going to collide with the bottom, and I'm also going to collide with the top. So those are the 3 sides that I'm going to be able to collide with if I happen to meet a tile with a value of 13. Now, the reason I have some of these functions nested inside of if statements is because I can only collide with one of those sides of a tile at a time. So I can only collide with the top, and if I do, I can't possibly be colliding with the left or the bottom. Certainly not the bottom if I'm coming from the top. How would I collide with the bottom? So I use these if statements to early out of my routing function and not have to execute checks for these other 2 functions, which is great because for any given tile, we're only checking collisions on sides until we actually do collision, and then we just exit out and we don't have to check the rest of the collision. So collide platform top is going to be in this if statement. If I collide with platform top, then I'm no longer going to have to check for colliding with the left side or colliding with the bottom side of the tile. Now inside of my narrow phase, my function returns true if I do in fact have a collision and it is resolved, and it returns false if no collision was detected and nothing was resolved. And if that's the case, if it's false, it'll just jump down to this next narrow phase collision method, call that. If there's no collision there, it will jump finally to the last method in the case and call that. And if that doesn't return true, then there is no collision and nothing gets resolved. So that's the routing function. Pretty simple. That's how it works. In previous tutorials on how to do this system's tile-based collision system, I used an array and I used object references to get these, but actually it's much faster to use a switch statement. So that's why I made the switch to a switch statement. Pun intended there. So anyway, next step, onto the narrow phase. Now let's look at the narrow phase, and that is going to be farther down inside of the Collider class's prototype. So inside of the Collider class's prototype, I have 4 functions, and those are collide platform bottom, collide platform left, collide platform right, and collide platform top. And awesomely enough, with these 4 functions, we can do collision detection and response with all of the different tile types. Basically any tile that has 4 sides, we can take these 4 functions and combine them to get all kinds of different combinations, up to 15 combinations, which is as many combinations as you can have with a 4-sided tile. So let's take a look at, let's see here, collide platform top, where I think I was on already. Let's take a look at collide platform top and see how this actually works. So from the routing function, you're going to get the object and you're going to get the top side of the tile. So the top side of the tile is just going to be whatever the top of the tile is that you're standing on. So right now I'm standing on this tile. I have my object, I have the top of my tile, and we're just going to run an if statement that checks to see if the bottom of our player character is greater than the tile top, and if it is, then we run this code. But wait, there's more. There's an and in here, so we've got to see what that is too. We're also going to check to see if the bottom of the player from the last frame of animation is above the tile top. Now, if you didn't include this, it would still work, but it would not work as smoothly as you see here. So let's go ahead and comment this out and see what happens when we don't use the old position from the last frame of the player character. I'm going to comment that out. I'm going to save. I'm going to come in here. I'm going to refresh. And now let's see what we get. Everything might work perfectly, but oh, wait, how about that? I just jumped right through that tile. Now, the reason for that is when I jump up, the top left and top right corners of my player are going to enter into this tile space. The broad phase is going to detect that. It's going to hand the information to the routing function, and the routing function is going to call collide platform top. Now, collide platform top, without doing this check on the last position that the bottom of the player was in the last frame of animation, without that, it's just going to check to see, is the bottom of the player greater than the tile top? And if it is, set it to the top of the tile. So that's what's happening. When I enter into the tile, it detects that the player was below the top of the tile, and it just sets it right to the top. So that's the functionality you're going to get without this. When you add this in, basically what's happening is it's saying, hang on, let me refresh real quick. Basically it's saying, okay, the bottom of my player may be inside of this tile, but if on the last frame it wasn't up here and therefore entering into this tile between frames, so on frame 1 he's going to be here, on frame 2 with the force of gravity he's going to be down here inside the tile, he's going to be entering in through the top, and collide platform top is going to detect that inside of this if statement because the bottom on the current frame is going to be below the tile top, and the bottom on the last frame is going to be above the tile top. So that's going to be true, and then we're going to get the appropriate response that we expect, and we're no longer going to jump through the bottom of the tile and get that kind of glitchy looking collision response. So now let's take a look at what happens after we do that, after we collide with the top of the tile. So I'm going to collide with the top of my tile here. This is going to be true. The bottom on the current frame is going to be slightly below. The bottom on the previous frame is going to be above. And what I'm going to do is I'm going to set the bottom of the object. I'm going to set this bottom of the object to the tile top, and I'm going to subtract this little value here. And I'm going to get into why I subtract that value in a minute. I'm going to take a look at another function because that better explains why I do that. I'm going to set y velocity to 0. This way gravity doesn't keep increasing and eventually pull me through the tile altogether. I'm going to set jumping to false so I can jump again. And I'm going to return true so I can tell the routing function not to do any more narrow phase collision calls. So now let's take a look at this little value and see what it does. But I'm going to do it in the context of the collide platform left function because that also has a similar problem. Collide platform right and collide platform bottom don't have this problem, and it has to do with rounding. So let's just comment this out and see what happens. But first, I'm going to show you the desired functionality. So right now I'm colliding with the left side of these two tiles, and it's calling collide platform left to do that collision resolution. So as you can see, I can jump up and down, and it's as you would expect. I'm jumping up and falling down. Nothing is broken yet. So let me comment this out and break the code. I'm not really breaking the code. It's all going to work the same. It's just not going to have the desired effect. I'm going to refresh my screen, and I'm going to come over here, and I'm going to do this again. Now when I jump, I land on top of the tile, and the reason for that is because when I'm falling down, I'm actually going to be in this tile space with the right side of my player. So the right side of my player, when I'm falling down into this tile space, is actually going to be in this tile space. Just looking at it with a naked eye, it looks like he's fully inside of this column, but really his right side is just barely inside of this column over here. So unless we subtract that 0.01 or some tiny number, doesn't have to be 0.01, it could probably be 0.1 or 0.001 if you prefer. Because we subtract that, we are pushing the player character out of this tile into this column, and he's no longer touching this after he enters or exits collision with the left side of this tile space. So let's refresh and see what that good functionality looks like. Now I'm colliding with the left side of this tile right here. It's pushing me out of collision, and it's actually pushing me out of the tile space entirely by 0.01 pixels. So when I jump, I am fully inside of this column as you would expect, and I'm no longer going to be colliding with these tiles unless I press right on my keyboard and move the player into them. So that's why I have to subtract that little value. Now, before I stop talking about the narrow phase collision, let me just talk a little bit about object.getOldRight and how we actually do that. So basically all we're doing is on every frame we are saving the last frame's player position, and we're getting the new frame's new player position. So where that happens is inside of the player object. Let me actually come out here and look so we can actually see the code a little bit. The player class now extends the object class, and inside of the object class we have, this is the object class right here. Inside of this we have some information to describe a rectangle, and we're also going to have the xold and yold values. So keep that in mind. We have a x and y location, and we have the x and y location from the previous frame of animation. So if I come down here to the player class and I come down here to his update function, this is where we're going to be keeping track of this. Xold and yold are going to be updated on every frame of animation to equal that frame's current x and y position, and then we're going to update x and y to be as fresh as possible in the new frame. So we're basically just keeping track of the player's old x and y position from the last frame and his current x and y position from the current frame, and that allows us to calculate his angle of trajectory, and we can see based on that trajectory if he was above a tile before he entered into it, and that will give us the ability to get rid of that broken functionality that you saw where I would jump up and just almost teleport through this tile and sit on top of it. So that's why we have to keep track of this. This is also great for interpolation, which is something really useful for smooth animation, but I'm not going to talk about that in this video. Anyway, that is the narrow phase. It's really simple. The functions are all really simple. If you just take a look at the source code, I urge you to go to the link in the video description and check that out on my GitHub page. And that's it. I'm going to show you how I added sprite animation to the game so you can take my example and use it to put sprite animation into your own programs. I'm going to talk about what's new in part 5. Then I'll give you a very simple and brief refresher on how sprite animation works when using a sprite sheet, and finally we'll take an in-depth look at the animator class and how it works with the player's movement to render the appropriate animations. Alrighty, so the first thing I want to take a look at in part 5 is the example program, and as you can see in this example program, I no longer am working with the little white and gray square. Now I am working with this animated rabbit, and he looks a lot better. It's starting to look a lot more like a game that you can actually play, just minus power-ups and items and stuff like that. So basically not much has changed other than I've added an animator class that does the sprite animation, and I've also tweaked his physics for jumping and stuff like that a little bit, but that's pretty common sense stuff. Kind of know how to do that if you're already to this point in the tutorial series. So I'm not going to worry about the specific changes I made for this video. Instead, I'm just going to worry about showing you guys how the animator class works to get this guy animated on the screen. If you do want to see what has actually changed in the code since part 4, take a look at the source code that I've linked in the video description at the top of each file that has changed. And for part 5, it's just these three: the game, the display, and the main files. For each file that has changes in it, I've added a bulleted list in the comments at the top of each file that outlines what exactly has changed specifically in the code. So if you want to find out what's changed, take a look at the source code and take a look at these comments. But in this video, I'm just going to focus on the animator class and how to get this dude animated on the screen. So stay tuned and I'll show you how it's done. Now let's take a brief look at how sprite animation actually works when you're using a sprite sheet. So this here is my sprite sheet image. It's a PNG, has all my tile graphics in it, has my sprite images in it. Now each sprite animation is just a compilation of these different unique images. So each image can be considered just a square that you would cut out of this bigger image and then put on the screen in quick succession to give yourself an animation. So for instance, right now my player character isn't doing anything, he's just sitting still. This frame is literally being cut from this position right here. If you notice, this and this are exactly the same image. So currently he is displaying this frame of animation. If I were to move him to the left, now he's going to stand still. He's going to be displaying this frame right here. When he's walking, it's going to give me an animation. So I'm going to be playing those frames over and over again in quick succession. It's kind of hard to tell because he's walking so fast, but he's basically playing, when I walk to the right, he's playing this set of frames right here. He's stepping through these 4 frames right here, and that's going to give me my animation. So what's happening is, on every frame that I draw to the screen, I'm going to see which frame that my player character's class is determining that he should show based on his movement pattern. It's going to take that frame, it's going to go into this tile sheet image, it's going to cut that specific frame out of the tile sheet. It is then going to take that frame and draw it to the player's location on this display canvas, this canvas element that I have in the browser window, and you're going to see whatever frame that is supposed to be displayed, and that's going to give you animation. So that's basically how it works. Basically, you're just cutting different images out of a bigger sprite sheet image, and you're displaying those smaller images at the player's unique location on the screen. Now we're going to take an in-depth look at what makes the code actually work. Or I guess we're just going to take an in-depth look at the code because the code makes the code work. So here I'm going to start with the frame class. Now the frame class is just going to define a rectangular region that we are going to cut our sprite images out of the tile sheet with. So it has an X value, a Y value, a width, and a height. And that's just going to be the source rectangle that defines the individual image inside of our sprite sheet. So I'm going to use one of those frame classes to define each rectangular region for each one of these individual images. So that's what the frame class is going to be for. And just bear with me as I explain all these different classes, and you'll see how they fit together at the end of this part of the video. So don't worry about the offset X and Y positions just yet. I'll tell you about those later. Just keep in mind it's just a rectangular region for the moment. Now we're going to look at the tile set class, and this used to be the tile sheet class inside of the display file, but I moved it over to the game file. Basically the functionality is exactly the same. I just renamed it and its location is different. Basically just keeps track of the number of columns and tile size of our rabbit trap sprite sheet image, and that's it. Where animation comes in here is with the frames array. So now we just talked about the frames class, which is down there. The frames class is just a rectangular region with an offset position. Each one of these values inside of this frames array is just going to be one of the rectangular regions that corresponds to a specific graphic for our animation. So for example, this frame is where the idle left graphic is inside of our sprite sheet. This frame is where the jump left graphic is inside of our sprite sheet. This group of frames is going to be where all of the individual graphics are for the walk left animation. Down here we got the walk right animation. So basically all I'm doing is defining each rectangular region for every one of my sprite animation components, or basically these individual images. So now you know where the individual frames are going to be defined inside of the tileset class. Now we're actually going to have to define what those animations are. So the animation itself is going to be defined by the object that's using it. So the animation for this rabbit, or for the player, is going to live inside of the player class. So every unique animation, the idle frames, the walking left and right frames, the jump frames, those are all going to be stored inside of the player class, inside of its prototype. So I'm just scrolling up to that. Here we have the player prototype, and inside of it we have an object called framesets. And inside of framesets we have all the different animations for the player. We have his idle left, jump left, move left, and then the rightwards motions for those different animations. So each one of these values corresponds to a frame inside of our tilesets frames array. So for example, idle left is going to have a value of 0 in it, and 0 is going to be the frame index, or the index inside of our frames array, where the rectangular region is defined to cut the image out of the sprite sheet for the idle left animation, and that's just going to be here. So this is index 0 inside of our frames array. It's idle left, and that's what we're going to use for the idle left animation of our player, and that's why that value is going to be a 0. So as you can see, each one of these values just corresponds to a different frame inside of the frames array. And what a frame is, it's just a rectangular region that we use to cut out our sprite sheet images from the sprite sheet. So how do we actually animate these? That's going to be our next class that we look at, and that's going to be the animator class. So I'm going to scroll up to the animator class, and I'm going to take a look at what this guy does. So here's the animator class. It's a frame rate dependent animation class. So what that means is the rate of frames that you see for each animation is going to be totally dependent on the game engine's frame rate. So if you don't want that kind of functionality, this probably isn't for you. But if you're just going to run your game consistently at 30 frames per second across all devices, this is probably what you want to do. And for HTML5 games, that's a pretty good bet. So this will probably work for you. So I define a couple different values in here. I have count, delay, frame set. Frame set is going to be those different frame sets, or those different animation arrays that I define inside the player. So for example, frame set could be, I'm going to scroll down here, it could be any one of these animations. It could be idle left, it could be this array right here, it could be move left, which is that array right there. It could be any one of those, and basically it's just going to use that information and loop through it when it does my animation. So, oh, I think I went too far. Here we go. So the frame set is just going to be one of those arrays with those values, and those values of course correspond to our different frames that we use to cut the animation image out of the sprite sheet. Frame index is just going to be where we are, or where the playhead is, so to speak, inside of that frame set array. Frame value is going to be the value of whatever index we're in inside of our frame set. So for idle left, remember that was value 0, the value was 0. So for that particular animation, it would be at index 0 inside of the frame set, and the value would also be 0 for the idle left image. And then we have mode. Mode right now for this example, there are only two modes. We have pause and we have loop. Now pause and loop are just going to be the two types of playback that we want our animations to do. So pretty simply, I'm going to just explain that as we go. I'm going to come down to the loop function. all it does is it just changes the playhead position every so many frames that pass in our game loop. So count is going to increase 1 time on every cycle of our game loop until it reaches the delay that we specify. So for the walking left and right animations, I've defined a delay of 5 inside of the player class. So every 5 frames of our game loop's animation or cycle, we are going to run the code inside of this while loop. So count, we're just going to decrease that by delay, and that makes us wait again. Frame index, this is where we set the frame index or the playhead inside of our animation. Basically, this we're just going to say, is the frame index currently less than the frame set.length? So let's take a visual look at what's going on here inside of our rabbit trap PNG. So let's say the frame set that we're going to use has values that correspond to the walking right animation, which is going to be these 4 frames right here. So frame index at 0 is going to yield a frame value of this image right here. At frame index of 1, I'm going to move over 1. It's going to be a value that corresponds to this image right here. When I move it over again, it's going to correspond to this image right here. So basically what the code inside of the loop function is doing is it's just increasing my frame index by 1 until it reaches the end of the frame set. And when it reaches the end of the frame set, the next time it goes to increase, instead it just sets it back to 0. So inside of my loop function, all that we're going to do is just say, set the frame index equal to the frame index plus 1 if it's not yet past the end of our frame set length, and if it is past the end of the frame set length, just set it to 0 to restart the animation loop over again. Then finally what we do is we get the frame value. That's just going to be the value that corresponds to the specific rectangular region that we store in the tileset's frames array that corresponds to the image that we're going to be cutting out of the sprite sheet. So the frame value is just going to be set to whatever our frame set array is, and we're going to hand in the index of the playhead. So whatever frame index is, that's going to give us the value inside of our frame set that we're currently at in the animation's loop cycle. Alright, so that was a mouthful, and hopefully I'm explaining everything quite well. I think the next place we want to go is probably the render function, but first I want to just touch on this functionality here, the change frame set function inside of the animator class. And basically what this does is it just changes what frame set we're using. So whenever I press left on the keyboard, I'm going to call change frame set. It's just going to change the frame set to the left animation, which is that array inside of the player class that defines which frames to use for the left animation. When I press right, it's going to call change frame set. I'm going to hand in the player's right movement animation. If I jump to the left, I'm going to call change frame set. I'm going to hand in the left animation. You kind of get what I'm saying here. Then the only other function in here is going to be the animate function. It just checks to see which mode we're in, loop or pause. Pause is going to be for no animation, so pause is going to be called on the idle animation, so idle right and idle left. Pause is going to be the play method that we use. For the walking animations, we're going to be using the loop method because we want to keep animating that cycle of frames over and over and over again. And basically this is just called on every frame, and it just calls the corresponding method. It's pretty simple. So now that we know how we're animating our frames, let's actually take a look at the render function, which lives inside of the main file, and we're going to take a look at how we actually use that frame information to cut our image out of the sprite sheet itself. So the first thing we do, we're actually going to have to jump to another section of the code real quick because I'm using an assets manager to load my tileset image. So real quick, I'm just going to jump up here, check out the assets manager class. All it is an image, and I'm going to load in an image with our rabbittrap.png image inside of it. So really all that we're doing here is just using the assets manager to load our tile sheet. Really simple. So that's all that is. Don't worry about it too much. You could write your own code. You don't need an assets manager. All you need is to load up the tile sheet image to use it for drawing from that tile sheet image. So here we go. Here's where we get the frame value. So frame, we're going to get the frame, remember, is just that rectangular region, but we're going to get to it through all those classes I just talked about. So the animation class is going to give us a pointer to a frame value, which lives inside of the frames array inside of the tileset class. And then the tileset class is going to be using the frame class to define its rectangular regions to cut images out of the tile sheet image. So how we get the frame is we just get the frames array from our game's tile set. Then we go ahead and we hand in the player's current frame value, which is kept up to date on every cycle of our game loop. Inside of the update function, we're going to be calling player.updateAnimation, and that's going to update our frame value inside of the loop function, most likely, of our animator class. So draw object is going to take all this information and put it together to give us the appropriate image that we need to see to make our animation work on the screen. So what we're going to do is we're going to hand in our source tile sheet image. Then we're going to hand in the actual source frame's X and Y position to cut from. Then this is going to look a little complex, but it's really not. We're going to hand in the player's X location and Y location. And we're just going to add basically an offset where we want the frame to show up and be drawn to the screen. So right now, the player's frame is slightly offset from the player's real location. And the reason I want that to happen is so when I stand on the edge of a tile, I actually fall through. And if you look, his ears on the frame are actually kind of moving through the tile. Or if I go over here, the image itself is actually overlapping the tile. I don't want it to be pixel perfect like that. I want it to be functional. I want the player to have fun. I don't care about pixel perfect collision as much as I do the player having fun. So this code, basically what it does is it just repositions the frame a little bit to center it on the player's position so we can more easily move him around the screen without that pixel perfect collision that makes his hitbox seem a lot larger than it needs to be. So all this does, it gets his X position, it adds the center, or it gets the center of where I want to draw that frame on top of the player by just getting half of his width, subtracting half of the frame source frame's width, and then it just adds the frame's offset X position. If I don't add that offset X position, and remember I was talking about that for the frame class, if I come back into the frame class all the way at the bottom here, we define the offset X and offset Y, and then when we actually instantiate each frame, we're going to add -2, which is the going offset Y position for this player. If I don't add -2, this is what happens. I just set it to 0. I saved. I'm going to come back in here. As you can see now, that was the Y offset. He's now 2 pixels deep into the ground. And that does not look quite right. So that's why I have that offset position. All it does is add a slight offset when I draw the frame to the screen to make him appear in the appropriate location. So that's it. That's all that does. You don't need this stuff. Like I said, I'm using a frame-based approach. You could easily use a tile-based approach where you have all your graphics inside of one big grid, kind of like the tiles are, instead of having them all close together and cutting them out specifically. The reason I do this is because if I were to add, let's say my rabbit has a sword, and the sword comes out to here, now my sprite is going to be different, and it's not necessarily going to fit uniformly into a box or into a grid row and column cell with all the other sprites. So I do it this way because sprites change. They change in size. They vary in size depending on what animation you're doing. So this is just much more flexible for me. So now let's get back into the rendering function. Went off on a little rant there. So basically all the draw object function does of the display class is just draw from the tile set, from the frame's X and Y position, and it draws to the screen whatever frame is currently in the animation, in the player's animation, draws that frame to the screen at a slight offset position. Then we call display.render, and that draws everything to the screen, including the tiles and whatever frame of animation our player is in. Alright, so now let me just quickly see if I actually missed anything here. I think I went over everything, how everything works. Let me take a look inside of the player class itself and actually see how we're doing the player's animation, how we're actually deciding which frames to display and which frame sets to use. This is going to be done inside of the update animation function. So update animation is going to be called on every cycle of our game loop, and it's basically just going to check to see what direction the player is facing, and it's going to choose an animation based on that. So the very first if statement inside of update animation is going to be, is the player moving up, which means is the player jumping up. So if I press up on the keyboard, the player is going to move up, and if you look closely, you can see that the up animation or the up frame is played briefly while he's moving up. While he's moving down, it switches back to idle left. So if he is moving up, and if his direction, which is determined just by which direction he's facing, so when I press the left key, his direction is going to be -1. When I press the right key, direction is going to be +1. So if his direction is -1, so if he's facing left, I'm going to change his animation frame set to jump left. If that's not the case and he's facing the right, I'm going to change his animation frame set while he's jumping to jump right. I'm going to do that in the pause position. Now for these other ones, basically, is he moving to the left? If he is, and his velocity is a certain amount, then we're going to play the move left animation. If the velocity is not a certain amount or less than that, basically if he's basically stopped and his velocity is very small, we're going to play idle left instead. Now this is cool because what this functionality allows us to do is it allows us to have our player gradually stop walking even though we're not pressing the walk key anymore. So if I were to come in here and change this code to, let's say this is the left walking animation. What is this? Move left. Let's change this to 2, -2. And I saved. I'm going to come up here, refresh my screen. Now let's see what happens for the walk animation. Because I have to be moving at 2, a velocity of 2 to the left, the move animation doesn't actually run unless I hit that 2 pixels of movement velocity per frame. So what this allows me to do is it allows me to create an effect where I gradually walk to a stop instead of just halting to a stop really hard like that. So a better kind of example would be if I used 1 instead and I refresh the screen up here. Let's see what that looks like. Now I start walking right away because I hit a velocity of 1 to the left really quick, but as soon as I stop, I go into the idle animation, and that's not really good because it looks like I'm sliding too much. Or maybe you do prefer that, and that's the great thing about this code. You can just do whatever you want. I kind of like it where I'm just going to gradually stop walking until I'm completely stopped. I don't prefer to just automatically stop and slide on my feet like that. So what I've done is I've just set a very small value for the velocity check, and if he is moving slower than -0.1 pixels to the left, then he's going to idle, and if not, he's going to continue walking until he just comes to that gradual stop like that. So that's pretty cool. So basically, the update animation function is fired on every frame after you do collision detection with the player in the world, and it just determines what way he's moving, and depending on what direction he's moving, it runs a certain animation. Now this is actually really important. It's more important than you think. Not necessarily for the player, because you can have fine control over the player, but for non-player characters who move on their own, you have to determine their animation based on how they're moving because you don't control them. You can't say, play the run animation when I press the run key because you're not pressing a key for a non-player character. For those non-player characters, you have to keep track of what direction they're moving, how they're moving, and based on that, you have to set their animation. So that's what this code does. It just automates the process of setting the animation. It doesn't rely on key presses or user input. It just sets the animation depending on what direction he's moving. Before I go any further with this series, I want to address something called tunneling. It presents major problems for any physics engine, and tile-based engines are no exception. Tunneling is sure to affect you, particularly if you are writing your own physics engine, so stay tuned while I talk about how to overcome this pesky glitch. Alright, so let's take a look at what tunneling actually looks like. So this is the Part 5 example program, and I haven't changed any of the code since Part 5, but I just want to show you this one glitch that happens underneath this T-shaped structure of tiles. When I am running into this tile from the right, so I'm pressing down on the left key and I jump, I actually pass into the tile. Now, I can actually jump down below the tiles and walk around because of the nature of my tile-based collision code, but obviously you don't want that to happen. This actually isn't a problem with the collision code itself. This is just a problem with tunneling, and it seems to happen just in this one scenario. So in order to show you guys better what's actually happening, first I'm going to explain what tunneling is, just using my mouse pointer as an example, and then I'm going to show you in slow motion, when I slow this game down, I'm going to show you what's actually happening with the player and why tunneling is happening in this particular instance. So tunneling is when the object moves too far in one frame to actually collide with a collision shape. So let's say that this tile is going to be my collision shape and the mouse pointer is going to be my object. So this is frame 1. On frame 1, my object is right here where the mouse pointer is. And on frame 2, I'm going to move my object a little bit to the left. So this is frame 1, this is frame 2. My object has moved about 16 pixels to the left. Now, this is okay because I'm not moving more than one tile space. I'm actually going to be over top of this tile space, it's going to detect that I'm colliding with it, and it's going to move the mouse out of the collision and put it back into an empty tile space. That's how it should work. Tunneling happens when the mouse moves much farther than one tile space, or 16 pixels in this case, over the course of one frame. So if this is frame 1, and I move in frame 2 all the way to here, what's happening is I'm jumping right from here all the way to here, and I'm never detecting a collision with that tile because I'm never landing in it. So tunneling is basically just moving a player object or any object too quickly to detect collision with a stationary collision object. So now that you kind of understand what tunneling is, let me slow this down and show you in action what the tunneling looks like with the player character. So I'm going to save my code. I'm going to set the frame rate to 1 frame per second. That's going to slow things down a lot. And I'm going to refresh. Now, as you can see, things are really, really slow. So I'm going to run over here into the corner, and it's going to take a while. So just bear with me. But I'm going to show you this glitch in as slow motion as I think it should be. I don't want to go any slower than this or it would take forever. So here I am. I'm standing next to the tile. I'm going to press up, and I'm just going to jump straight up. So I jumped up, and immediately this tile up here resolves collision and throws me right back down below it. But if I jump up while I'm pressing the left key, I jump up and I move slightly to the left. Now, that's when the tunneling occurs. So the tunneling isn't actually happening on this tile right here. It's kind of a special case, but I'll show you why. So I'm going to run back out here, and I'm just going to jump up. The tunneling is actually happening when I jump because the player character is moving about 20 pixels upwards as soon as I start jumping, and you'll be able to see that when I jump here in a moment. So if I could actually get this thing to comply, it's just moving so slowly. All right, so I'm going to jump and just take note of where this player actually moves to when I jump. So this is the top of the player right here. This would be 16 pixels from the ground right here. When I press the jump key, immediately my player is above that 16 pixels. His feet were about right here, and he clearly moves more than 16 pixels, which is our tile space. So if he can potentially move past one full tile space without stopping in it, he can tunnel. Because tunneling is basically when on frame 1 we're out of collision, on frame 2 we jump over a collision object and never touch it. So what's happening here is when he jumps, imagine what happens if he were standing right here. He's going to jump up. On the first frame, the top of his hitbox is actually going to be over top of this tile, and the bottom of his hitbox is going to be inside of this tile. So what's happening is when he jumps and he's standing here, he's going to jump up. He's not even going to have a chance to collide with this tile because the top 2 corners that I'm checking on his hitbox are over top of this tile even. The only reason collision happens on this tile is because his 2 bottom feet, or his 2 bottom corners, are inside of this tile. And he can still technically move to the left while he's in this tile because collision is only going to happen in this tile with the bottom side of the tile. And it does. When I'm standing underneath this tile, it does do collision, but just on the bottom side. I can still move to the left. So when I jump up underneath this tile, I'm going to jump, I'm going to hit my head on the bottom, and it's going to send me right back down again. But remember, I'm jumping 20 pixels high, so what's going to happen is just my feet are going to collide with this. When I jump, I'm actually going to move up here, then it's going to place me back down there, and I can still move over to the left. So when I jump up and press left, I'm actually going to be up here, and I'm going to fall back down into this tile on the wrong side of the collision boundary. So that's what tunneling is, and there's a really easy way to fix it. If I come in here and I set this back to, let's see, 30 frames a second, that ought to do. Let's see what that looks like. 30 frames a second, things are back to normal. What I'm actually going to do is I'm going to come out here and I'm going to change the speed at which he jumps, and that's actually going to fix everything. So if I can find where that is, oh, it's actually in the game object here. Let's see, jump. I'm actually setting jump. Whenever he jumps, I call this function, and it moves him 20 pixels up. It sets his Y velocity to negative 20 pixels. So what I'm going to do is I'm going to set it to negative 15 pixels. And that's going to prevent him from ever moving more than one tile space. And actually, I'm going to set this back to 1 frame so you guys can see that in action as well. Let's go back to 1 frame per second, refresh, and now we're going to zoom in and take a closer look at this guy jumping. So this is what 16 pixels looks like when he jumps. As you can see, his bottom feet are no longer way up here on that first frame. On that first frame, they're down here, so he'll still end up colliding with this tile right here. So when I move back into collision, and I'm going to speed things up for this, set it back to 30 frames a second, save, come over here, refresh my page, and now tunneling can no longer happen. So collision is going to happen as I expect it to, so that is the problem. And I guess I kind of showed you how to fix it in the first part, but I'll go into more detail on how to fix it in the next part. Okay, so we just looked at part 5's example program where we had this glitch where, actually I fixed it, but very fresh, we had this glitch. And I'm going to leave that in actually, so if you ever check out part 5, that glitch is going to be left in there. But now I want to show you a better way to fix it, and this is a sneak peek, if you will, at part 6, where I actually did fix this problem. So here's the same exact tile structure, same scenario in part 6, without the glitch. Now, how I did this was I basically just clamped his movement velocity to never exceed 16 pixels or 1 tile space. Now, if you just reduce the amount of velocity that he jumps at, it can cause problems. So, for instance, here, I'm going to take a look at part 5 again. Here's part 5. I can jump up above this tile if I have a Y velocity of negative 20 pixels per frame when I jump. So obviously, if I reduce this to 15 and I save, it's gonna eliminate the possibility of tunneling. That's great, but now I can't jump up on my platforms anymore. So how do I fix this? Well, the way to fix it is to go ahead and change your gravity and friction. At least that's one way to fix it. So I'm going to save that so it's back the way it was. I'm going to come over here and I'm going to take a look at the code. Excuse me. I'm going to take a look at the code inside of part 6. So in part 6, I'm still using a velocity of negative 15 when I jump. The only difference is now I'm clamping my movement velocity when I update the player's position. So basically to do that, I'm just saying if the absolute value of the player's X velocity or Y velocity is greater than some max velocity, and that's going to be 16 or 15, basically our tile size, or maybe one less just to be safe. If it's greater than that, then we're going to set our velocity to the max velocity. And actually this code is wrong because I don't want to change the sign of my velocity. I just want to change the amount of my velocity. So, but you get the idea. Part 6 is still in development. Basically, what you want to do is you want to clamp your movement speed, and to get the same jump height with the different Y velocity, what you do is you just reduce gravity and friction. So here is what a jump looks like in part 5. As you can see, he jumps a lot faster. It's kind of almost too quick. So this is almost an improvement for visuals as well. And this is part 6 where I've kind of changed it up so he can have a clamped velocity, and he just moves a little more smoothly if you look at it. It's a little more smooth. Here's part 5 again. Jumps really far, really fast. It's a little bit too quick. Part 6, a little more smooth. Hopefully you can pick that up with my video recorder here, because sometimes it doesn't quite match the frame rate of the game when it's recording. So basically what you want to do to fix tunneling is you want to clamp your jump speed. So the amount of velocity that you apply to a jump, and that's going to be where a lot of your velocity comes into play. High velocities when you're jumping, that's going to be a thing. You want to clamp it to an amount that's less than 1 tile space. Then in order to get the height of the jump that you want, you're going to have to reduce gravity and friction. So for me, I came in, when I define the world object, what I do is I just have gravity and friction defined here. So for example, friction, if I change the value of friction to say 0.99, that's going to be really low friction. So if I come over here and refresh, now I'm going to have really, really low friction. And as you can see, I'm just moving really fast all over the place. Jump really far, really fast, because there's no friction. So I don't want that, but that's basically how you fix tunneling. You just basically have to clamp your velocity to a certain speed, and to get the jump height that you want, you just mess with friction and gravity, and that's going to do it for tunneling. I'm going to show you how to create level data files using JSON, how to load level data and use it to populate the game world, and finally, how to trigger subsequent level loads by colliding with doors. Let's take a look at what has changed since part 5 and part 5.5. So this is part 6, and everything is basically the same. I did make quite a few changes, but most of those changes pertain to loading different levels. So when I jump up into this area here and walk off the side of the screen, it's actually going to load a different level, as you just saw. So how this is working is I have a little door hit region just off the right of the screen here, and it's just a rectangular box, and when the player character's center point hits that box, it loads the level and places the player in whatever location he needs to be to start this level out when walking through that door from the other level. So basically in part 6, I just have a couple different levels, and I've defined a couple different types of doors. They're all just rectangles. You just saw 2 small rectangular doors. This area on the bottom of this level is one big rectangular door, so I can jump up through it at any point in this rectangle. So this system works great for any size door. Doesn't just have to be 1 tile. It can be any size rectangle that you define. So that's basically part 6. So now that you know what the example program is about, let's get into how this works. Before we get into the JavaScript code, let's actually take a look at the different level files. So this would be level 00, or I call it zone 00. So the file to load this level that you see on the screen is this file right here, zone 00, and basically it's just a couple of different JSON structures. So I have a doors array, and inside of that I just have the doors that are contained in this level. So for this level, level 00 or zone 00, I have one door just to the right of this tile. The door would be right here off the level that you see on the screen, and this JSON here defines an array of doors, and this object inside of it will be that door object that resides right over here. So that's my doors array. Down here I have some information about the maps. Each map has 12 columns and 9 rows. I did not format this so you could actually see it in kind of a 2D row and column format. I just have it in one big long array, but if I were to line this up so each row had 12 columns in it, you would see that the maps are 12 columns by 9 rows. But this is my graphics map, so these are all my graphics tile values. This is my collision map, so these are all the collision values for the tiles. And then finally I have ID, and that's just going to be the level ID. So like I said, this is zone 00, so when I load zone 00, this just tells my world object that it's zone ID 00. So now let's take a look at zone 2, and we'll just take a look at zone 2's code really quick, just so you get it in your head that this is what the format is. So here's my doors array. Zone 2 has 2 doors. There's a door right here to go back into zone 0, or actually it's zone 1. Excuse me. because I start labeling as 0, but this is zone 1, and it leads back into zone 0, 0. There's a door right off the left side of the screen here, and it goes into zone 0, 2 with a door right over here on the far right side of the screen. So inside of my doors array, I have defined 2 door objects. And then, same as before, I have my columns and rows and my 2 maps and the ID that just indicates what zone this is. So if you know how to write JavaScript, you know how to write JSON for the most part. It's really easy, and it's a really great natural fit for writing information that you're going to load into your JavaScript game, because it's so similar to JavaScript already, and you have the built-in JSON.parse method to parse this information into usable JavaScript objects. So now that you know how to write the level data, let's get on to the next part of the video. Okay, so now that we know how to define our level data, we need to figure out a way to load it. And the best way to load it is with XML HTTP requests. So inside of my main.js file, I have a class called Assets Manager, and it basically just has a function called request.json inside of it. So in order to load my JSON file, I'm going to call this request.json function. I'm going to pass in the URL of the file to load. So basically, if I want to load zone 0, 0, I'm going to pass in the string zone00.json, and I'm going to provide a callback function, but I'll get to the callback function later. So first thing I'm going to do is create an XML HTTP request. I'm going to give it an event listener for the load event, and I'm going to have an event handler for when it loads, which is just going to call my callback and hand in the parsed JSON string from my JSON file. So I'm going to send off my request to the server. It's going to process it. It's going to hand me back the file content. Remember that file was zone00.json. It's literally going to hand back this stuff in response text or just text format. And I'm going to take that response text or the content of my JSON file. I'm going to use json.parse to turn it into a JavaScript object, and I'm going to call the callback. So that's the request.json file that we're going to use to actually load our data. So now let's take a look at where we first load up a level when we first start the game, and that's going to happen all the way at the bottom of the main.js file in the initialization section. So this is where we're using the request.json file to load up our very first level. So when I click refresh, my code is going to run in main.js, and this right here is going to be responsible for loading up zone 0, 0, which is on the screen right here. So let's just take a look at what we're handing in. Calling assetsmanager.request.json, zone prefix, that's just going to be the string zone for the first part of our URL. Game.world.zoneID, when I first instantiate game, it creates an object called world. So game.world is a world object, and that has a default value in it of 0, 0 for world 0, 0 or zone 0, 0. So that's where we're going to get the 0, 0 from. This is going to be 0, 0. And zone suffix is just going to be .json. So I have the zone prefix of zone plus the game.world.zoneID, which is 0, 0, plus zone suffix, which is going to be .json. So I'm going to hand in that URL to request.json. It's going to send a request to the server. When the server returns the JSON data inside of zone 0, 0 in text format, I'm going to parse it into a JavaScript object, and then I'm going to hand that JavaScript object into my callback function, which is just going to be defined here. I defined it in arrow function format. So this is my callback function, and remember that I passed in json.parse request.response text. So that's going to be the JavaScript object that I created from my zone file. And I'm going to hand that into game.world.setup. So let's go ahead and take a look real quick at game.world.setup, and also where we create the very first default value for zone ID. So let me see if I can find where I'm at here. I'm inside of the game file, and this is the game.world.prototype. So let's go up a little bit more. Game.world. This is where we define game.world. Let me real quick just take a look at the default value for zone ID. So remember, the default value for zone ID, we're going to use that right here when we're loading our first level. So that's just going to be defined right here. Right now the default value is 0, 0, so when I refresh the page, the first level it loads is 0, 0. If I change that to say 0, 1 and save it, and refresh the page, keep an eye on the level map, it's going to load up world 0, 1. If I change it again, let's go world 0, 2, save, we're going to load up, and it's going to immediately, well, it dropped us in world 2, but we fell down into world 3, so basically this sets our default level to load initially when we boot up the game. So that's where we define that, but now we're going to take a look at game.world.setup, where we actually put all the information from our zone file into our game.world object, which we use on every frame of animation to do stuff with our game. So down here is the setup function. This is game.world.setup, and it takes one parameter, which is the zone, which we just parsed into a JavaScript object from our zone00.json file. So basically, all we do is copy over all the values from our newly created zone object, and we copy those values into our world object. Pretty simple. The only one we don't copy directly is the doors array, and the reason for that is because I want to use a door object that I define. I'll talk about that in the next part, but we do loop through all the doors in the zone's doors array, and we just create a new door from the doors that we loop through. So inside of this zone file, we have an array called doors. Every object inside we get, and we convert this data into a game.door object. So this class here, we're just going to create a door object from the door data inside of our zone.doors array. So whatever door we loop over in that doors array is going to be converted into a game.door class, and that's what we're going to use for our actual game logic and game physics when we collide with the doors and stuff. Now, we finally know how we're setting up the very first initial level. I'm getting out of breath here, I'm talking so much, but now we need to know one more thing, and that's how to actually go ahead and load a level on the fly when we walk into a door. So where we do that is inside of the update function for the game. So on every cycle of our game engine, on every game loop, so to speak, we're going to call this function from inside of main, and this is the update function. So the first thing we do is get some user input. Then we call game.update. Game.update takes care of moving the player, takes care of all the world collision. And inside of the game.update function is the world.update function. So let's go ahead and take a look at world.update real quick. Already inside a world, game.world.prototype. So this is the game.world.update function, which is called inside of the game.update function, which we're calling right here. So basically, this function is going to call this function. So first thing we do is update the player's position. We collide the player with the world. This refers to game.world. So we're going to collide the player with the world, so all the tiles. And then we're going to come down here and we're going to loop through all the doors in the world, in the current region or zone of the world. We're going to get each door, and we're going to test for collision with the door. And it's just basic rectangular collision. I'll cover it in the next part of the video. Basically, if we do collide with the door, so if the player actually collides with the door, we're going to set this.door or game.world.door equal to that door that we just collided with. So normally this.door is undefined. So out here in our update function, which is called on every frame, we're going to test to see if game.world.door is not equal to undefined. And the only time it's not equal to undefined is when for a split second we actually walk into it. And then this if statement returns true, and we go ahead and load the world that was specified by whatever door we collided with. So let's just go through this real quick and see what happens. The first thing that happens when I run into a door, so if I run into a door, the first thing that happens is I stop the engine. I then make a request with request JSON to whatever zone that door brings you to. So if I come up here into my zone00.json, we're in zone 00. the destination zone for this specific door, located at an x of 192, which is about there, and a y of 64, which is about there, has a width and height of 16. So right off the right of the screen here is a box that's about 16 by 16 pixels. And when I collide with it, it's going to load zone 0, 1, and it's going to put the player at destination x of 0, and -1 just means we're not going to use destination y. So the player's y destination remains the same, but I'll get into that in the next part. So basically, we're going to request the destination zone specified by that door. So this door here that we're about to walk in, right to the right of the player, will tell us to go to world or zone 0, 1. So when I walk into it, this code loads up zone 0, 1. Pretty simple. The same thing that we did for the initial level load, we're just doing again right here. Even have the same arrow function with the zone parameter specified inside. Then inside of our callback after request JSON, requests the level data. The server gives it back to us in text format. It parses that into a JSON object called zone and hands it back to us. We're just going to call game.world.setup, and it's going to get all the information out of the level file and put it on the screen basically. So there is one difference this time, however, because now we're going to have to use some information from a specific door. So let me go back inside the game.world.setup function real quick. I'm going to scroll up to it. Right here, game.world.setup. And we check for the case that we are colliding with a door. Because remember, when we enter into collision with the door, we set the world's this.door property equal to the door. So when we call setup, this.door is actually going to be equal to whatever door we just collided with. So if I come over here and collide with the door that's right over here, it's going to be equal to that door that I just collided with. And it's just going to set the player's X and Y center position to whatever the door's destination X and Y values were. And that's it, really simple. Everything else works the same as the initial level load. The only difference is when you walk into a specific door, you reposition the player according to that door's destination X and destination Y. So stay tuned for the next part where I'm going to talk about the door class specifically, the collision, and all that kind of good stuff. Now I want to take a look at what a door actually is. So if I zoom in here, I'm going to look at what a door is inside of my zone00.json file. I've got an X position and a Y position, a width and a height. So basically, my door is just a rectangular region on the screen somewhere that the player object can collide with. Then I also have a destination zone. That's going to be where the player is going to go, what level I'm going to load if the player hits the door. And I have a destination X and a destination Y for the player as well. So this is where I'm going to put the player in the newly loaded zone when it loads. If I have a -1, that just means destination Y does not get used and the player's Y position remains the same. Same thing for X. If I have a -1, the destination X position isn't going to be used. The player's X position is going to remain the same. So we can see this functionality over here if I fall into this world. I'm not being repositioned on the Y-axis, or on the X-axis rather, because I don't need to be. I just want to fall right through and naturally have my player end up where he has to be based on where he was in the previous level. I don't want to jump through this floor door right here and end up at the very start of the door over here in the next level if I jump through over here. Like if I jump through right here, I don't want to come out in this world right here because it just wouldn't look right. So that's the only reason I have a -1 there. But anyway, let's look at the door class, the game.world.door class, and actually see what that looks like in the collision code that I'm using to have the player and the door actually collide. So if I could find that wherever that is, I'm going to scroll. Hopefully I'll come across it soon. This is it right here. So it's a really simple object. I'm going to correct that small formatting error there. Really tiny object. Basically is the same exact thing as this right here. It just has a prototype defined with the collide object function inside of it. So this is the door class, and I'm going to call object on it. Object, all it is a rectangle class that has some functions for helping me determine the sides of a rectangle. So it has functions like get left, get right, get top, get bottom. Just defining a rectangle here, inheriting from the object class. Then I'm going to set the destination X, Y, and zone to whatever those are from the door object that we hand in. And that's just going to be whatever is defined inside of the zone file. Then inside of the prototype, I have a function called collide object, and that's just going to test to see if the object's center points are inside of the rectangular region of the door. So this code right here just tests to see if the player is not colliding with the door. If he's not, then I'm going to return false, and that means we didn't have a collision with the door. If any of this is true, or actually if any of this is false, then we know that we have collided with the door, and in that case, we're going to return true. So where do we actually use this? That's going to be inside of the world.update function. So if I come down here to world.update, right here, there we go. Okay, so inside of world.update, I have all the doors defined inside of my world.doors array. I'm going to loop through every door in that array. I'm going to get each individual door. I'm going to test to see if the door is colliding with the player object. And if it is, I'm just going to set the world's door property equal to that door. And then, just like in the last part, we're going to go into the update function for our main game loop. And inside of that, we're going to have an if statement that just checks to see, is game.world.door defined? And the only time it's defined is right after we collide with the door. So we're going to stop the engine. We're going to load the level defined by the door's destination zone more specifically. We're going to set up that zone in game.world.setup, and we're going to restart our engine. Now inside of setup, and I know I'm recapping stuff that I just talked about, but inside of setup, we have, this is the inside of the setup function, we have an if statement that just checks to see, is this.door or game.world.door defined? Is it not undefined? If it's defined and we have a door in there, we're going to set the player's X and Y coordinates equal to whatever those were defined as by the door object. And if it's not equal to -1, then we know we can set it up. If it is equal to -1, we just leave it alone. So that's like in this case here, where I'm not changing the player's X position. So for both of these doors, this door up here and this door down here for each level respectively, the destination X position for that door is going to be set to -1 because I only want to change the player character's Y position. This way I don't have him jump through here and start out over here on this door. So that's basically it. That's how I define my door objects, and that's how to load levels with doors. I'm going to show you how I define the carrot and grass objects in the level data file, their respective classes, and the basic collision detection used to collide with the carrot objects. The first thing I'm going to talk about is what this example program is all about and where the carrot and grass objects are defined, because since the last installment of this series, I've since added carrot objects and grass objects. You can see that I'm running into the carrot objects, and when I collide with their hitbox, I collect a carrot. I have a carrot counter at the top left of the screen, and then down here I have some grass objects, and all the grass objects are just objects with an X and Y position, and they have an animator inside of them. They extend the animator class, and it just updates the image on every frame of the grass to give the impression that the grass is actually swaying back and forth. So just some basic objects that I've added. And if I come over here and take a look at the zone file, you can see that this is my level data file, and I have an array for carrots and I have an array for grass, and basically they're just little arrays inside of here that define an X tile position and a Y tile position. So if I come over here to my map and I refresh, this carrot is going to be at position 1, 2. So the X tile is going to start at 0 and go to 1, because this right here is 1, 2. So X tile of 1, Y tile of 2. So if I count from 0, I get 0, 1 on my X tile axis, and for the Y tile axis I have 0, 1, 2. So I know that from this map I want a carrot at position 1, 2, and that's that carrot. Same thing for the grass. My first grass tile is at X position 2, Y position 7, and that's going to be this grass object right here. So pretty simple. So when I load my level up, I'm going to actually have to loop through these arrays here, get the X and Y tile positions from them, and then create an object from that X and Y tile position. And if I am looping through the carrots array, I'll create a carrots object. If I'm looping through the grass array, I'll create a grass object. So let's go in and check out the setup function of the game.world object. The setup function just runs, if I come over here and refresh my screen, the setup function runs right after the level data is loaded. So right after I load this level data and I get access to it with json.parse, I then call the setup function. I pass in the JSON object that I just parsed after I loaded that level data from JSON, and I go ahead and I set up all of the game objects and the graphics and collision map and everything for this level. And then I'm going to go ahead and I'm going to loop through the zone's carrots array and the zone's grass array. And basically those are literally just going to be these two arrays right here. So I'm going to loop through them and I'm going to create a new carrot and a new grass object for every instance of one of those little X and Y tile arrays that I come across inside of the zone file. So what that looks like is I'm just going to use a for loop. I'm going to go ahead and I'm going to loop through all the carrot objects inside of my zone's carrots array, which is just the little tiny X and Y tile arrays. I'm going to create a carrot object, or not an object, but a variable to store that X and Y position from the zone.carrots array. And then I'm going to store a new game.carrot inside of my game's actual carrots array that I'm going to use on every frame of animation inside of my game cycles or my game loop. So what I'm going to do is I'm going to feed it an X position in pixels, not in tile space. So I'm going to take the X tile position of the carrot, which is located at position 0 inside of that array that we loaded from the level data, and I'm going to multiply it by the tile set.tile height, which is 16 pixels, plus 5 is just going to give me an offset. So if I were to come out here and make this plus 0 and save, I come over here, what's going to happen is I'm not going to have an offset of 5 pixels anymore, so you can see they're kind of offset to the left by 5. If I come back in here and I undo that, the Z, Control Z, save, come back over here and refresh, now all my carrots are in the right position, pretty much. I do the same thing with the grass. Basically, I just loop through all the grass in the level data file, and I create a new instance, a new grass object, and I just position it based on the X and Y tile values stored in my level data. So that's it. Next, I'm going to take a look at the actual classes that we use to make the grass and carrot objects. Now we're going to take a look at the grass and the carrot classes, respectively. So first, I'm going to start out with the grass class. And all it is really simply an animator object. It inherits from animator. This way I can animate the frames, and it also has an X and Y position. If you look at a grass object, which is just this right down here, obviously all it does is sit in a location. So that's going to be my X and Y position, and it is animated. So it's going to have to inherit from the animator. Now the animator class is the same class that I use to animate the rabbit. It can be reused for all different kinds of game objects to give them an animation. So really simply, the grass class just has an animation and a position. And the carrot class kind of does too, but it also has a lot more. So let's go up and take a look at the carrot class and see what makes it move and how we collide with it with the player object. So here's the carrot class, and it inherits from the object class, the game.object class, as well as the animator class. So the animator class just gives it the animation. The object class is what's going to give it its X and Y position, as well as its width and its height. And in addition to those things, it also gets the collide object function, which is going to be responsible for allowing us to collide with a carrot and actually collect it. So that's important to note. Then some cool features about the carrot. We have the base X, Y, and position X, Y values. So base X and base Y are just referring to the center position that the carrot is rotating around, or making that figure 8 around. So that's going to be the base X and base Y position. The carrot does still have an X and Y position. That's going to be where it's actually drawn to. The base X and base Y are going to be just the point that it rotates around. Position X and position Y are going to be vectors that the caret is placed by the amount of the vector on whichever axis away from the base X. So to explain that a little more clearly, if base X is in the center, position X and position Y are going to be distances away from the base on their respective axes, and that's what's going to determine how far from the base the caret is. And we're going to, I'll show you how I'm using position X and position Y in a second. I'm just going to move down here, but I set a random value up here, and that basically just makes all the carets kind of have a different path, because otherwise, if I just set this up to be, let's see, 0, all the carets would have the same rotation pattern. They'd all be synchronized, basically. So if you look now, you can see very clearly that they're all synchronized, and that's kind of a bad look. So just go back to how it was before. Save, and now you can see that they all kind of move independently, and it's a lot less jarring to look at, because before it was almost like there was a big, just solid image of carets with the transparent background just moving back and forth on the screen. And that's not what we want to go for. We want to have independent movement. We want to have things looking like everything is random. So also, speaking about that, up here, the frame index, if you notice, all the carets on screen are not sharing the same animation sequence. Well, they're sharing the same frames, obviously, but if you look at 2, you can see that they're animating at different rates. I just have to find 2 that are going at offset values here. These 2, this one and this one, they display the opposite frame from one another. So when this one is on frame 0, this one's on frame 1. When this one's on frame 1, this one's on frame 0. And that keeps things looking fresh. So if I come up here and change this to just be 0, it's going to reduce the randomization, and we're just going to have everything animating the same exact way, almost like it's updating from the same exact animation object. So that's not what we want either. We want things to randomly update their animation, not randomly, but look like they have their own unique animation, even though they're displaying the same frame. So to do that, all I'm doing is I'm starting off the animation at a randomized frame index. All right, so now let's take a look at what actually makes these things rotate around the base X and base Y position. Inside of the game.caret.prototype, which is going to be the prototype for our caret class, I have a function called update position, and that's the only function for this class. And this is going to be called on every frame of animation. We're going to talk about this in the next part, but all it does is it updates the position X and position Y value, and sets the actual X and actual Y value of the caret object, which we're going to use to draw it to the screen. So, excuse me. Position X and position Y, what it does is it's just a distance from the base. So you can think of it as a vector distance from the base. So, oh, actually, well, that is true, but when I'm updating these, it kind of controls the speed of the animation. So if I were to make this 5 and this 9 and save, we're going to see the carets move a lot more quickly. So when I press refresh up here, now they're really moving. Like, those guys are jumping around quite a bit there. So that controls the speed at which things move, because on every frame of animation I'm adding 0.5 or 0.9 to these, and that's going to make the thing move a lot more quickly, obviously. So let's get back to how things were. Save. Come down here and look at how we actually use these. So math.cosine and math.sine are what's going to give us that circular motion, and we just plug in position X and position Y into cosine and sine. And over here we have a multiplier of 2. That's going to control the distance that the caret sways on the x-axis. So if I come over here and refresh to get things back to normal, you can see that it sways a little bit further from side to side than it does from top to bottom there. So the reason for that is because of this 2. If I were to make this a 10 and save that, the carrots are going to sway a lot more from side to side than they do right now. So now you can see they're really swaying from side to side, but that looks kind of ridiculous, so we don't want that. But basically what's happening here is we're just we're incrementing up position X and position Y. Math.cosine and math.sine give us a nice rounded or circular kind of effect there, and then the multiplier is just going to be how big is that distance vector from the base position. I guess it's actually a scalar because it's only one single value, but together they make a vector. So let's just put that back to 2. So on every frame, I'm going to call update position, and this code is going to run, and it's going to make the caret move back and forth. Now, if I refresh, everything's back to normal. So next, I'm going to talk about how we actually do the collision between the caret and the player. To do the collision detection between the player object and the caret object, we need a function that basically just does collision detection between 2 square hitboxes. So where that function is inside of game.object. So I'm going to scroll up to game.object, and we're going to take a look at the function that we use to do that hit detection. So here's the game.object.prototype. That's just the prototype for our game.object class, and we have collide object. And what collide object does is it just tests for square collision detection between 2 rectangular objects. So this object is going to collide with the parameter object that I hand in. So basically I'll be able to hand in 2 objects and determine whether or not their hitboxes are overlapping. So just wanted to show you this function, and now you'll kind of know where the collision detection function is coming from. Where I'm actually utilizing all this is going to be inside of game.world's update function. So I'm going to come all the way down to the bottom, all the way down past the player object, past the tile set object, to the world object, inside of the, not the setup function, but the update function. So here we are inside of the update function, and here we are going to call all of this code on every frame of our game's animation. And we start up, we update the player's position, we collide the player with the game world to get the tile collision going, and then we're going to start colliding with carets. So we have a carets array that's going to hold all of our caret objects that we created inside of game.setup, or game.world.setup rather. We're going to loop through all of those caret objects, so just these guys here, and we are going to update the caret's position. We're going to animate the caret, and then we're going to say, is the caret colliding with the player, with the collide object function? If that function returns true, we're going to splice that specific caret out of the carets array, and we're going to just remove it completely. And we're going to add 1 to caret count. And it's as simple as that. We're just going to test for collision between the player and the caret. If collision occurs, we're going to just remove the caret. The caret object is totally gone. It will be garbage collected later on, assuming that I removed all references to it. And I think I have. So then what's going to happen is I'm going to increase caret count by 1. And caret count is what we're using to update this p element's inner HTML right here. So where does that happen? That happens inside of the main.js file. If I come down to the render function, I have a p element. It's referenced with the p variable, and I just set its inner HTML to equal carets plus game.world.caret count on every frame. And that's it. So I hope you guys learned something. I hope you enjoyed the video, and I'll see you guys next time.